preliminary ideas about how one could, in principle, conceive a quantum model for time perception. And this is something that I've been discussing with in a diverse team and open-minded team composed by my colleague neuroscientist of the University of Pisa, Maria Concetta Morrone, and Marco Cicchini from the CNR in Pisa, and Jorge Iagomalo, a really brave, I should say, quantum physicist who has joined us really a few months ago. So I will share with you some preliminary ideas, and first of all, maybe it's important to understand where this kind of diverse environment came from. And actually everything started with the conception of a proposal where also Sabrina was involved, IQ Minds, integrating human and machine minds for quantum technologies. Actually, Sir Roger Penrose yesterday reminded that Pisa is very famous for the Leaning Tower and for Galileo, but in fact we also have one of the largest artworks of Keith Haring that is called Tutto Mondo in Italian, that means all world. And IQ Minds, in fact, is a quantum black box that is aimed to problem solving or optimization of problems otherwise non-tractable with other means, that is equipped with quantum technologies, with interfaces, with measurement tools and citizen science tools. So the idea is to conceive video games as interfaces, and here was where our neuroscience colleagues were involved, along with the computer scientists and also game developers and quantum physicists and physics education researchers were involved. So use video games to channel the human power in terms of visual mind, creativity and intuition, with all the words just taken care of as Demis just showed us, to train either classical or quantum computers. So this is where everything has started from, but discussing how to model, possibly model visual mind and human visual behavior for conceiving these video games in a proper manner, we came across a set of experiments on time perception that are run in Concetta's lab, and so we started thinking that it could have been valuable to try and see whether we could use the beauty and the many possibilities that the quantum physics provide us with to describe some of the strange phenomena that happen when perception of time is considered. And so in the logic of the presentation, I will first look, maybe following on some of the concepts that Sabrina discussed yesterday about quantum effects in biological systems. We heard also many things today also from Stuart, for example. Then I will provide some examples of these experiments on time perception and how this diverse team of quantum physicists and neuroscientists started conceiving this coarse-grained, very coarse-grained model, quantum model for time perception. And given the diversity of this audience, I thought that it could have been valuable to provide us with a kind of a tutorial on how these quantum models in real-time dynamics they work, and build some intuition, then to see to which extent possibly some preliminary ideas about how this can be used to build a quantum local clock. And so let us start with with the quantum effects in biological systems. In fact, in this presentation, I will, in the spirit of the conference, I will really make contact with many of the ideas that have been discussed so far, also with the intention to possibly create some additional contacts for the future. And so here are two very recent and I think very beautiful reviews that we have been discussing with our slow science group with Bert, Paavo and Sabrina. One is the one by Grigory Scholes and others, where it is shown, for example, from one of the most recent experimental results. This is excitonic fluorescence from a polydiacetylene molecule that shows beautifully these quantum coherence interference patterns over something like 10 microns. So it's really a beautiful result that is a way of stating, as also Sabrina was discussing yesterday, how in fact these macroscopic quantum coherence phenomena take place in biological systems, even though it's not yet clear whether they play a functional role, and this is the main issue. And then there is also this other beautiful review by Bethany Adams and Francesco Petruccione, Quantum Effects in the Brain review, where in essence they describe, they review a lot of literature that is now available about possible occurrence of various types of quantum effects that are not only coherent charge transfer, but also entanglement, spin effects, inelastic tunneling, and in which kind of neural realizations these can take place in the brain. And of course here this is a picture about, so my laser pointer doesn't work. This is a picture that in fact schematizes how coherent charge transfer could happen within the colored areas in a coherent manner, and in incoherent manner across these shaded areas. This is something that has been proven in FMO complex, but for example, this could also be the microtubuli, actually the tryptophan molecules in Stuart's and Sir Roger Penrose's case. And over time scales that go indeed from picoseconds to seconds or even hours. Of course, since I'm going to speak about time perception, we also need some higher level, and so I couldn't, it was for me inevitable to mention something about consciousness, and since I'm going to use quantum models, I really need to remind what has been really very inspiring for me since when I've been reading The New Emperor's Mind, about the inspiring idea of Sir Roger Penrose that quantum superposition of simultaneous alternative locations separated in space-time geometry could be a mechanism, as has been discussed also today by Stuart, a mechanism for consciousness that, along with what Stuart showed us today about the possible microscopic mechanism, could provide us with the time of the being that would happen when at a time that is h bar divided by the difference in gravitational energy between the possible alternatives. And up to here we get an algorithmic, as we discussed, we saw algorithmic function of the mind, and then a non-computable, of course, with all the caveats that Demis gave so far. Very inspiring to me, because this is something, this idea is something that puts together three of the most fascinating mysteries that humankind would like to solve. That is why quantum physics works so well, how does gravity works, and how our mind works. So let us look at this time perception phenomenology, and this is a painting by Salvador Dalí that essentially tells that sensation of time, feeling of time, is illusory and distorted. But this is not just the creativity of Salvador Dalí in synthesizing this concept, but is a reality in experiments. Because indeed we are so highly able to discriminate and to judge time. And I think we will have a beautiful example of this tonight with music performance, both for the players and ourselves as listeners. But we don't have a specific and direct sensor of time. And on the other hand, we also know there is a vast literature we were discussing also yesterday, stating that we are not equipped with just one clock in our mind, but we are equipped with many clocks, a multitude of clocks that also interact and are linked to space and time perception. And so this makes things quite complicated. So I'm going to ask you, please, to stare at this open dot, while in a moment what will happen is that this circle will start blinking, and then after some time there will be a second circle coming here, and then a third here. Please look at all the scene, and then I will ask you a question. So this is blinking at some frequency. Then we look at this, and then which one between the second and the third lasted longer? Yeah, unfortunately, the real duration of the lasted longer, the second, this one, right? So this one, the real duration of the upper one was 600 milliseconds, but our perception after the adaptation of the visual mind to the blinking of the first circle, our perception is shorter, is compressed. In this experiment, was something between 450 and 500 milliseconds. If we add, for example, the gaze, so we move eyes during this kind of experiments, then we can get even an additional compression. And there is also a link between, if you wish, I can show you other experiments, but for reasons of time I won't do it. There is also a link between compression in time and compression in space. And also the other message that I want to convey is that our mind works like if we had not only one clock, but in this case, at least two clocks. And also that this is not just proper of the visual system, but of any sensorial system we are equipped with. And this is another kind of experiment where we have two stimuli, 1 and 2, and then a third and a fourth, separated by something like a second. And the duration of the first two is, say, tau, that is here in this graph. And the duration of the second is tau plus delta tau. And if we go and see which is the shortest time that we can discriminate, we see that for all kinds of experiments, this is, first of all, we have a compression, and this happens irrespective of the fact that the stimulus is an auditory stimulus. In this case, we are able to discriminate something like 2 milliseconds, or a visual stimulus. In this case, we are able to discriminate something like 10 milliseconds, or a mix of the two. Then in this case, we do a bit worse, but still we have a compressed sensation of time. Okay, so the message is that brain-mind, depends on the perspective, works as if they were different clocks, and time intervals can result to be compressed in a way that is linked to space, also to space visualization, and that as a rule of thumb, this is, all this is valid for any sensorial network and also their combination. So, of course, we heard today and also yesterday that there are various manners, various kind of modelings that can be used to explain this kind of experiments. What we know, really the essential things that we need for this kind of experiment are taken, this slide is taken from a nice paper by Buonomano and others. What we know is certainly that neural circuits oscillate, that there is a rich dynamics as a consequence of this, that it can confer, in fact, a time ability at a local scale, but in order to have this, we really need to introduce not only an excitatory mechanism, but also an inhibitory mechanism. Otherwise, a time delay, the inhibitory mechanism, otherwise it's impossible to take care about this kind of effects. And also we know that usually brain functions are typically modeled with artificial neural networks, so that, schematically have an input and in the layers and output, and that these can be trained to solve specific tasks. For example, here, to recognize a car independently of the perspective, we look at it, but maybe for now at least, they can fail and confuse this colored area with a person. And so, but for now, okay? So what I would want to say is that we are just looking at a different approach, just to try. Life is fun. And so I'm going to introduce this coarse-grained quantum model that is really, has been really conceived along the lines that Sabrina was discussing yesterday. So really a very coarse-grained, minimal model. And the idea is that maybe we can afford it for this kind of experiments because we can use the beauty of quantum physics. And so let us see which are the various levels that we can, of modeling that we can use. Of course, we can model the information, we can model the neurons as nonlinear filters and the network of the filters. We can model the neuronal architecture and model the microscopic biophysics and chemistry, but if we wish to stay into a very minimal model, we stay in this domain. And how do we do the mapping? We really take the essential properties, and so we have neurons that can be either active or non-active. In our quantum physics language, we have a spin up, neuron active, or down, non-active. Then we have a propagation of activity that for us is a tunneling between nodes of the network. And we have a built-in connectivity of the network with an excitatory and inhibitory mechanism. What I learned in these months is called in jargon receptive field or inhibitory surrounds by neuroscientists. And for us, this is an interaction potential between the nodes that we will take in the form of a Mexican hat to take account of this excitatory and inhibitory function. Then we want to possibly have a flexibility in modeling the connectivity of the nodes. Sabrina was discussing yesterday how geometry and topology is important. And for us, this will, we will make two extremes of this topology. One is a nearest neighbor, so means each node is connected only with the nearest neighbor. And on the other side, the all-to-all, so each node is coupled to all the other ones. Because we want to eventually have the possibility also to introduce different functions, the modeling of different functions. And then our neurons can decay to a resting state that for us means putting in some dissipation. So physicists, when they model something, they write down an Hamiltonian, that is the operator that provides the time evolution for the system, and this is our Hamiltonian, where the tunneling term means that for our spins, let's imagine to have an excitation, a spin up inside J. This is lowered inside J and recreated inside I. And so this is the tunneling with a J amplitude. And then we have the interaction potential in the form of this Mexican net that takes into account the excitatory here and inhibitory mechanism here. That is an interaction between two excitations at site I and site J. Then we have dissipation that can be in terms of particle losses, so we can project out in our quantum simulation one spin out of the coherent state, that means getting some quantum decoherence, and we do this at random places at random times. And still at random places, at random times, we can just add a dephasing that, especially with the all-to-all connectivity, will take us eventually to a classical kind of network, because we also want to see which is the difference. Of course, we can do something fancier than this, and I will come back to this later on. This is a very well-known model. It's called the XXZ because it is sigma plus, sigma minus can be written as a sigma XX, sigma Y plus sigma Y, with equal couplings. And we know everything from Yang and Yang in 1966 about the equilibrium properties of this model that takes to ferromagnetism, antiferromagnetism, the entanglement of the spins, and it is a paradigmatic model. But here we have a system with dissipation, with a real-time dynamics that has no trivial stationary state. And so we need to gain intuition about how this works. And then we have the connectivity. This can be nearest neighbor or all-to-all, and to be a bit more precise, this is the cartoon that Jorge has drawn. Nearest neighbor means something like this, and all-to-all means something like this, and independently of how many links we have, if we take out one neuron, this will interact with these linked partners via this Mexican hat. So let us gain some intuition about how this works. So this is really the simulation, the quantum simulation, in the case of the nearest neighbors and in the case of the all-to-all. In the simplest case, because in physics we add a complication at a time, so here there is only tunneling for now. But we see immediately the difference between the two. So in the case of the nearest neighbors, the spins have to tunnel one site, one node after one node, before getting rebounded into the boundaries, and then come back and have these revivals and collapses. While in the case of the all-to-all, that in principle one could say would be the messier of the two, instead we get a really very clean oscillation of our magnetization. What happens if so what we are doing here is that we are exciting one spin, one neuron, and then looking at how this how the magnetization, so the excitation, amplitude excitation works. And so this is just with tunneling, we just saw it. If we add the interaction potential, then this is a really small amount of interaction potential. Nothing happens in the earlier times, and then the oscillations, they start changing at longer times. If we take a wider Mexican net, then we are coupling much more and much better all the nodes, and then we have additional oscillations, and if we add the particle losses, then we have an amplitude of the oscillations that is decaying away. But what happens in the all-to-all is still that we stay with this very good oscillation. And so, of course, the point is that one more point that I think is important is that if we then add a second excitation, for example, here at time 12 in these units of tunneling, then you see in the all-to-all, so in the nearest neighbor, everything is messy. But in the all-to-all, you see we get a second frequency. And this is very important because we are looking for a clock, for a quantum clock and a local quantum clock. And so I'm going now to describe first ideas about how we can use this simple model to make a clock. Let's go into the frequency domain. And again, the simplest case, just tunneling. You see what happens. So the blue is the nearest neighbor connectivity, and the orange is the all-to-all. And we see that as soon as we add a new excitation, the system, this is the real-time dynamics taken after a long time from the excitation, but the system is able to, the neural network, quantum, is able to count these excitations and to keep memory of the number of excitations that have been created. If we add, same happens if we add the interaction potential, simply the peaks will be lowered. And this is also what happens if we add the quantum decoherence or the classical, like, say, dephasing. Only that, as also Sabrina was pointing out yesterday, quantum decoherence is not always that bad, even in this case in which we are using a kind of Markovian, so without any memory effect, a kind of modeling of the quantum decoherence, because you see that in the case of the quantum decoherence, the peaks are less lowered than in the case of the classical light dephasing. And so that these oscillations, they tend to stay there. Here is an example that is precisely the kind of protocol that is used in the experiments of in Concetta's lab, in Pisa Vision lab. So 3 spikes, 3 excitations, and we see that every time we add an excitation, we add a frequency that then keeps lasting for even in the presence of dissipation. If we look instead then at the magnetization, so the level, the amplitude of excitation, we look at something more complicated from the quantum point of view, that are the correlations, the sigma x correlation. So we are looking now at how and whether and how a sigma x excitation, so not sigma z, so not in the direction of the excitation, or in an orthogonal direction. We are in a quantum domain, so the operators x and y, sigma x and sigma z, do not commute with each other. And so we are looking at whether a sigma x excitation created at time t1 site I can be correlated with another one at site j and time t2. And this is a quantity that contains a lot of quantum information. And we see that our oscillations are really still there. They are in a kind of, this is a kind of an harmonic oscillator. This is a damped, underdamped one, and this is an overdamped one. Underdamped in the case in which the Mexicanette is the same size, order of magnitude than the dissipation, and overdamped if it is the interactions are larger, but still the oscillations are there. And what is important is that, also important is that at each given time t of the first, of the subsequent evolution, the height, the magnitude of these oscillations increases with the time t1 of the second excitation. That is something that is reminiscent of what neuroscientists call the Weber's law, that essentially says that time uncertainty, the time uncertainty in our perception of time, increases when the time increases. So it means that I have less uncertainty about something that has happened a few seconds ago than 1 year ago. So messages, and I'm going to conclude. How I'm doing with time?
You're good for conclusion.
Great. Perception of time is a useful playground to benchmark coarse-grained modeling, and also that this quantum clock model is promising for some basic perceptual phenomena that maybe are not so easily describable with other models. We have these two consistencies, so the persistence of the signal, so the ability of the network to count the excitations, and also this monotonic response to time t1, the Weber's law, that are important points for the time perception phenomenology. But what I really want to share with you more are the questions that are of two types. We have methodological questions and we have speculative questions. Methodological, first of all, we need to make some improvements in the method we are going to use to extract meaningful quantities from these complex quantum networks that are temporal complex quantum networks. So there is a lot of literature for non-quantum complex networks for these things, but more is needed in the quantum domain. Then this is needed, a needed step to be able to quantitatively link these results to the phenomenology of the perception of time. And then, of course, we can ask which distinguished features of the quantum case with respect to the classical case can be useful to explain whether they are, important to explain this phenomenon about time perception. And then, of course, extend the approach to build a full neural circuitry, which means also adding more sensorial domains that can be linked to each other, time-delayed feedback, for example, with non-Markovian kind of noise, and so on and so forth. Just an inspirational point, this is a more recent paper, Entanglement of Quantum Clocks Through Gravity. The idea here is to have a network of quantum clocks, but our spins, each spin is a quantum clock, because as an oscillation, can be considered as a two-level system with a difference in energy delta E that then provides us with a minimum time that we can measure. But what happens if these clocks are in a space-time? As is related to the inspirational idea of Sir Roger Penrose. And here the point is that since energy is mass, then this, if the way this clock is measuring time is precise, the other ones in the space-time, the ends of the clock are very fuzzy. So this brings a time uncertainty. And so this quantum superposition of each clock in the two energy states plus GR, general relativity time dilation, brings a time uncertainty that depends on the gravitational constant, the speed of light, and is inversely proportional to the distance, spatial distance between the clocks, and goes with time. And if we play the game with many clocks, a decoherence time induced by gravity enters in, that goes as one of the square root of n, and this is what happens if we take 10 to the 23, so an Avogadro number of these clocks together. So this is something that we can use for our first speculative question. This is the last slide. What about quantum clocks network under the combined action of quantum and general relativity laws? What about quantum clocks entanglement and entropy? Because they will have these properties in dissipative real-time dynamics, and whether this model quantumness has some implications on the microscopic, on the quantumness of the phenomena. So the possibility, for example, to lower the coarse graining of our quantum modeling like it has been done for FMOs. So I'd like to thank my slow science group. There is no picture because it's a slow science. Sabrina, Paavo, Bert, and we had as a guest star Jussi once. We meet once every 2 weeks to discuss about this beautiful kind of physics without any agenda. That's the reason why the slow science group, and of course, thanks to every one of you for this sharing.
Thank you, Marilu. In the spirit of motoring on towards supper time, any questions? I think we're going to pick maybe just one, because remember, Marilu is not going anywhere. We're all going to be at supper. There's more time. I think we have Bert speaking next, so as Bert gets ready, we have some time for questions if anyone's got anything that they're wondering about. I have a question.
Yeah.
This is actually, unfortunately, I saw that Giulio just ran to the washroom. But so, on the outside of, not the sort of the orc OR side of things, but it's maybe unfair to ask this without Giulio in here. But
then I can discuss with Giulio at supper.
But so, I mean, these are two very different conceptions, right? I'm not sure what's being accessed in orc OR version. Like, I'm not sure what's being accessed. What can we look for in the system, like the brain, and how to see something that Giulio would think should be there? Like, how do we do that? That's the part that I'm never really. So, like, do you understand my question?
Yeah, I think I have understood the question, and in fact, it's something that we have been discussed 2 days ago when Giulio gave
you were at the
workshop,
Helsinki,
in the Helsinki workshop. So, and there was also a question to Giulio this morning, sorry. That is about whether one can embed some quantum theory. Quantum theory in his IIT theory, and so he said yes. So he said yes.
Yeah.
And in fact,
Mari, you can mention also we read the paper, the Zanardi.
Yes, indeed. The point is that. Once, he's talking about information, right? Building up information. There are many ways of measuring information, the information content in a quantum system. I would expect that at the time in which he can make the quantum version of the IIT, then those notions of entanglement entropy, and that also require a different way, perhaps, of measuring the content of information will come about.
Yeah.
And I guess that
Giulio, I asked a question about you in your absence. That what does Marilu think he could measure, sort of in your kind of context? How could she try to quantify the sorts of things that you're trying to get a handle on?
So I was reporting about, I don't know whether maybe Giulio wants to tell about the Paolo Zanardi's paper that we were discussing.
Less about tonight.
Okay, thank you, Marilu.
Okay.
Thank you. All right. Thank you very much. I think that the connection is really quite real. Demis, we really should get a kind of a quantum protein folding discussion going. Yeah, it really will be
I was
interesting.
already anticipating a little bit, though maybe we could have a few minutes to discuss.
You pointed in our quantum chemistry paper that's going to come out.
Yeah, no, I'd love to see it.
Accepted in science, so that will be coming out soon. I want to connect the two.
Yeah, I mean, my interest, of course, is more related to the
How are you doing,
way
Basil?
in which you can model
We're almost done.
because what we are also working on are models of quantum environments.
Really?
Where you have
No, because I mean, I've always been. No, and that's sort of like.
That's what we've been doing with our quantum chemistry. BFT, trying to functional, learn the functional, so it's obviously approximating the quantum system without being quantum itself.
Exactly. But this is
Kind of interesting, it's almost the reverse of what you're doing. You're building quantum systems
what I
while you're
think.
classical.
We discussed this morning, and I actually think that there are ways to reach this. In a way that on the one hand you have a more microscopic description, which includes some more level of quantum is still constrained, where you have parameters that are free and that you can optimize, but it does include a certain, let's say, modelization, which might be useful in order to give also to have like some predictive powers. Because of course, of course you can recognize folding and so on, but you can't really say, well, if I give you a certain environment, how will it fall? Yeah, exactly. How will it fall?
But I think we can solve that.
Yeah, okay.
It is. No. You have to do it. Otherwise, how?
But there are evidences
Or we lost
of
that.
certain specific
We've lost our
Yeah, but yes, they might be actually, exactly. But we've actually, what I'm saying is we've actually tried quite a lot of experiments along the lines you suggested of going positions and there are some positions, weird ones where it gets confused, right? So it's not got, I don't think it has a full understanding of the world champion doesn't, and it can't explain itself. So it's something, it's still more like a tedious amount than a top lower player, right? So you're right, you still haven't bridged that gap fully, but it's a lot closer than it used to be, right? So it's general, I mean, it's definitely generalizing enough that it could be a world champion in a new game. Obviously, the world champion is not trying to trick it. He was trying to play a proper game of Go, right? But he could have tried something sort of random and seen if it would have worked. And general random doesn't work. So some kind of systematic. We have another version of AlphaGo that's trained to right? It's quite interesting. So it sort of wins if it by confused we mean move by move. We can make it very volatile, the activation function, and we know it's the normal version of AlphaGo is a bit confused because it shouldn't be changing its opinion move by move, right? In a massive way. So we actually call it a sawtooth evaluation. If it's sort of oscillating between I'm in a good position, that's a terrible position, then it's sort of basically it's kind of confused, right? So we actually have another one. We actually it's quite interesting in experiments. We have it's almost like an exploiter system. That's a different version of AlphaGo that tries to exploit the first version. And we can actually use that to push the main AlphaGo system into weird distributions that it can learn from. So do you see what I mean? So when it gets better by playing against these exploiter algorithms. Yeah? So that's one way of pushing its experience out of normal distribution. Although interestingly, in advanced numbers, when you compare it playing chess, for example, against say Fritz, like a program, Fritz analyzes usually millions of moves per decision it has to make. AlphaZero is only about 10,000 per decision. So it's getting closer. Grandmasters only do about 100. Look at about 100. We don't work like Monte Carlo tree search, right? So we only look at maybe a few hundred. So it's actually AlphaZero starts to become much more human-like in the sense that it's using its neural network to kind of narrow down the search space.
All right. Right, folks. I think we've. Do I have everybody? I think we almost do.
Massive number, brute force.
Yes, we do. So I think it's time to move on to the talk by Bert Kappen, who will talk to us about quantum-like models. So without any further hoo-ha, I give you Bert Kappen.
Thank you. Thank you, Jussi. Thank you for being such a wonderful host and such a good tsar of this meeting, keeping everybody in time, and also being very hospitable here in this wonderful place. And also would like to thank Paavo. Where's Paavo? Paavo's over there for helping to organize this thing. So yes, I'm going to talk about quantum-like models. And walking over here a few days ago, I was struck by this thing. So I just found out. I was thinking, why are we having consciousness meetings in Finland? But apparently the whole town is already buzzing about it. I came across this walking over to Tononi's workshop 2 days ago. you do not have a soul, you are a soul. You have a body. So it's the arrow going from the experience towards the physical. So it's already, you know, it's out there, right? So we're on the right track. I'm happy that we're in sync with the community here. So one of Demis's last slides is actually one of my first slides. It's Feynman's blackboard, and you know, it's on the top left. What I cannot create, I do not understand. And so, like Demis, I'm also from the machine learning philosophy, let's say, and I've been working for 30 years, neural networks, machine learning, all kinds of things, in part because I wanted to understand what's going on here, how it is that I perceive beauty, the joy of music, chats with friends, all these kind of important things. And at the end of it, I have come with my AI to sort of this picture of the brain with like this gigantic clockwork that we can make. We can do chaos theory, we can do cellular automata, we can do throw statistical physics at it, we can do many things. But it somehow doesn't cut it, right? It's somehow at the end of the day, it's not sufficient. And so this inspired me to look further, and I want to share part of that journey with you. So here's a sort of a schematics which may raise some eyebrows, and maybe we don't have time, or maybe we do have time tonight. It's going to be a very intense night, I think. So here's sort of a picture of what kind of modeling you can do, right? You can do classical physics, you can do probability theory, and you can do quantum, right? So what is the difference? What are the commonalities? So in the classical, you have a state which is the variables in your system, the positions of the billiard balls, let's say, or the 3 dimensions of the Lorentz attractor that you're modeling. And so you have a dynamics that is like this, or in discrete time it's like that. In probabilities, you have a probability distribution which assigns a number to each configuration. So this becomes a very much bigger thing. So now x is the same vector of x of configuration, but now for all configurations, you need to assign a number, right? So this is a much bigger thing, and this thing satisfies Fokker-Planck equation or some sort of a Markov process. And in the quantum case, you have something very similar. It's like the probability distribution, but instead of assigning a number to it, you assign a complex number to it. And the dynamics is slightly different, although it's also linear, and you can have also kind of this kind of unitary dynamics, right? So, okay. So, here you have no superposition. Here you have superposition, because if you take a linear combination of 2 probability vectors, you have again a solution, because it's a linear equation, like in the quantum case. Entanglement, you have, of course, not in the classical case, but you have some sort of entanglement here, in the probabilistic case, right? Because if you have a ferromagnet, it can be in the superposition of up to up and down, down. And if I measure one being up, the other one is up. If I measure one being down, the other one is being down. So this is kind of entanglement. But there's a yes here, because there's a bigger entanglement in the quantum case. Bell inequalities. Of course, here's no Bell inequalities. Here there's Bell inequalities. So you get weird things. You get deviations from probabilities that make this more interesting than that, in a sense. But I think really an important distinction is the complexity. So the complexity of this is polynomial in n, in the number of variables, the size of the system. The complexity of this is exponential in n, like this. This is like this is marked because you have the complex numbers. Then locality. So this is local. So if I want to see what is particle 1 doing, I just look at its position, end of the story. Here, if I want to know what particle 1 is doing, I have to trace out all the other particles in a probabilistic way, sum out all the rest. And the same in the quantum case. I have to sum out all the rest. So you get non-local properties in this sense. So here you have particles. Here, if you deal with probabilities, you don't have particles, but you can simulate. So we have Monte Carlo sampling. So we have an intuition. We can take our ferromagnet and just flip some Glauber dynamics and get the states up, and it takes some long time to go to down, down. But we have that dynamical picture, which looks like a version of this, like many versions of this. Like instead of one trajectory, you have many. And that gives you the distribution. Here we have no sampling, right? So that's hard. Although there are subsystems that are quantum for which you can do sampling, but I'm not going to go there. But in general, you don't have that. So classical, we think it's the description of reality. So these are the billiard balls on the billiard. Here we think of probabilities, they don't really exist. They're descriptive. So if I flip a coin, there's nowhere in the universe there's a probability distribution, there's just outcomes. And the probability is just in my head. Here we have, well, I mean, the camp is divided. Some people think it's reality, like Sir Roger over here. Some people think it's more descriptive, like maybe Bohm. So that's a little bit of the background put in context the kind of way I'm thinking about this. I want to give you two examples of things that I've been doing, and one is really not very deep maybe, but it strikes me extremely intuitive, and it's my 5 cents towards consciousness. And I call it the dialogue of two realities. And so suppose I have this. There's a blank slide here. Okay. So suppose I have this child here sitting here, doing sensory motor control. Right. There is a lot of sensory things coming in, and then there is motor control, so moving the blocks, and there is this sort of constant feedback of sensory and motor things. So now there is the sensing, there's the perception. There's a lot of things going on. There is sound, there is touch, there is sight, there's all these kind of things. And the brain, I think, at any time cannot really pay attention to everything, so it has to make a focus in the attention. And so this focus of attention helps to filter out by making a prediction, essentially, what's going to happen, and in this way sort of filter out the things to attend to. So a nice example of that you see, for instance, here. If you look at a face, what your eyes are doing is actually scanning the face. So if it's on the mouth, it sort of has a model that says, well, here should be eyes, let me look there. And making the sequential eye movement thing is going to get you the recognition of the face. So it's an example of how prediction is making, so you're not scanning like a camera, everything, you make this predictive model. Another example is cocktail party effect, where it's very crowded and very noisy, you can selectively make attention to particular speeches as are going on and filtering out all the rest by using some predictive model. Now we can model this very nicely in a Bayesian way. So we say, okay, we have a standard Bayesian story, we have a brain which is a variable x, is a very high dimensional set of neurons, we have a y which is a stimulus, and then we have a joint probability of x and y which measures the correlations between the brain state and the perception. So x could be x1 to xn, the neurons in the visual cortex, and if you write p x1 given y, then this is the way that the neurons in the brain respond to a particular stimulus y. Okay, so this is this model. So now we can trace out all the stimuli, and we get a distribution over x. This is a distribution of a brain state, and you can think of this summing out as what happens in the history of the child is doing the sensory experience and doing all the sums. And so this is like the experience, this is the model that results from the experience of past sensory stimuli. And so this is then the prior that we get in the brain about how we think that our model of the outside world is called prior. So then, then we can write this joint distribution as a distribution, a prior distribution times a likelihood, what is called a likelihood term. So this likelihood term is a conditional distribution that is like looking out from the brain. Given that the brain is in a state X, what is the distribution of sensory things that are going to be out there, right? So that's that. And now, so of course now we can do the Bayes rule that says, okay, given now this model, if I now have a particular stimulus y, how does x look? Well, it's a product of the prior and the likelihood, right? So so the way that you respond to a stimulus is a product of prior and likelihood. The likelihood is giving the stimulus information, the actual thing that's happening now, and the prior is saying, well, how likely is that from past experience, right? Now the fact that something like that is going on, you can see very well in this example of a Necker cube. So here are two things, and in fact you can see these in two ways, and I've drawn two of them to help you guide it, but you can see it as this square being on the front and this being up high, or you can see it actually this square being on the back, and I don't see it at the moment, so it goes back and forth. So there's this double illusion, double thing, right? And so the way to think of it in a Bayesian way is that there is this bimodal distribution which represents these two shapes, and actually the stimulus in this case, the p y given x, is not very disambiguating the prior, and so our brain is stochastically hopping between these two states, and this is what's happening. So this is an example of that. Now if we have time data, of course the prior becomes a time series, so that's x now, it's not bigger, it's over time, and our sensory inputs are coming in at each time step, and so we now, the perception now is that you say, okay, I observe all these perceptions, and I want to predict what is the next state, and you can compute it by this Bayesian way, and you use this prior model. Okay, that's perception. Now what about action? How are we doing on time?
Good.
Yeah, goodish.
Goodish, but great.
Okay, well, so computing action. So action is control theory. So and basically, so here is this problem that this giant wants to crush this little man here, and I want to get you into stochastic control theory. So that is why is noise important in a control problem. So consider this spider want to go home, and it can either go walk over this small bridge or can walk around the lake. And if there is no noise in the problem, you will take the shortest route and you will go over the bridge, and that's the end of the story. Now, if there's noise in the problem, as we all know, spiders they hate getting wet, so the probability to fall off the bridge becomes positive, and so the cost incurred here becomes very large, and the optimal trajectory is now to walk around the lake. So the morale of the story is that if you add a little noise to a problem, the solution doesn't change a little bit; it changes qualitatively, like a phase transition. And in fact, that's what happens. So suppose we have this control problem here, that we want to move from an origin to one of two locations. And here is a dynamics, very simple. It's just a Brownian motion with a control term added to it. And the end position at time t is the initial position plus the sum of all the increments that I get here. And the cost that I have in this control problem is that I want to minimize the control cost that I exert and get onto the target which is specified by that, right? And in expectation, because I have noise, I have to average over that. Now this problem is actually quite hard, and if you have to solve it by what's called Bellman's equation, so and here's the solution of the Bellman equation. This is space, this is time, this is space, and this is this cost to go quantity. There's a scalar that has to be computed from a partial differential equation, and it shows that here is high, here is low, and here's even lower. It shows, and the control is the gradient basically. So the control is steering towards the middle here, and then at some point it is diverging, it's bifurcating to one of the two solutions. And if you draw trajectories under the optimal control in this model that I just presented, you get these kind of trajectories, and this is the optimal control. They don't look very optimal, but that's because you cannot control the noise, so the noise will stay always the same. Now there's another way to compute this. And that is to say, okay, let me draw trajectories from the uncontrolled dynamics. So there's no control is zero, just random trajectories like this. And let me color the trajectories by a cost, which is how good it does, good it gets to the end. And so then I get this cloud of trajectories, which are drawn from this uncontrolled dynamics. I get this. And in a sense, these two clouds are identical. Can be shown. And so this is something called Gazanov theorem. And so there's a long story here, but in fact what you see here is this is in fact a path integral. This is an integral over trajectories, and this whole control theory is formally related to the Bellman equation. Can be linearized as a sort of a imaginary time Schrödinger equation, and then this path integral is a solution of the Schrödinger equation. That's how this control problem gets solved. Now, the reason so you can do this in practice, and it leads to very nice fast applications. So here you see this car racing, and here you see the trajectories in the future, and they are used in real time to compute the control of this car, which is and so this is a real time, very high dimensional, stochastic, nonlinear control system, which is very challenging, and so this is done by people at Georgia Tech University. So this is okay. So this is a nice theory for control. So does it also? There's also evidence in the brain that actually this is a mouse or rat. I think mouse or rat. I always forget. Running on a track, and so there's place cells in the brain that code for position. But while it's running, there is also these simulations of these trajectories which are highlighted here, which is sort of used to control for the mouse. So this is the cell number, this is position, this is the cells, they're moving like this is where the rat is moving over this, but while it's happening, it has like these hallucinations where it's doing this. So in this hallucination, it's walking in the direction of where it's walking, and here it's walking in the retrograde direction. And so this is also So this you can do in mazes, but I have a video of that, but due to time I think I'm going to skip that. So it's showing the same thing. So this way of computer control is actually by considering forward trajectories. So we have now two operation modes, so perception and action, and we have a world model, which is the prior, and then we have, so in the perception case we do the Bayesian inference in that world model. In the action case we use the same world model to generate future trajectories to compute our controls, right? And we're constantly in this perception action mode, and we're using, and we have, so important to highlight that we have only one world model, right? This world model is the model of everything that if you're in current state, what the next state is going to happen. We're not going to have two in our minds, right? Because it's too big, it's very, very, very massive, right? So our whole brain is basically used to get such a dynamical model. So one model, which is one set of neural activities, and it's used in a switching way to be perception, so to look at the objective reality of the outside world, and a moment later to generate trajectories which are going to be used to compute our actions. And so these modes are different, right? In the first mode you sort of get an objective reality because it's very much constrained by the data that you get from the outside. In the second mode it's just a hallucination based on your own prior, which for every one of us is different because we have different histories. We come from different places, right? So there's a disjunction between these two realities. And so if you are walking around the street or talking to people, for me it's very intuitive, this idea that you're switching between these two realities, like these two movies. One is coming from outside and the other one is you're generating yourself. They're slightly different. And this difference between the two gives you a sense of identity, or at least a sense of uniqueness, right? Because it's switching between something that's objective and something that's subjective. Okay, that's my 5 cents about this story. Okay, so do I have another 10 minutes maybe?
Can we make it 5?
Okay,
you know
7.
Try, yeah.
7. Okay.
Sorry.
Okay,
sorry,
so
I'm just trying to hurt us all. We made a schedule.
Okay, so what I've been doing last year is to build one of the things. So there's been many things going on in the quantum area, and one of the things we have done is build a Boltzmann machine at atomic scale. So this is this is maybe the world's smallest Boltzmann machine. So these are atoms, individual atoms. They're shown by scanning toning microscopy. And what this system does, and what's very interesting, is that it has different time scales, and they vary differently, by factors of 1,000. So here you see that if the system is in this state for some time, and this is activity of these 3 neurons, where these 4 neurons are in a particular frozen state, and then spontaneously they switch, like they go from 0, 0, 1, 0 to all zeros, and then these 3 neurons do something different. So we have 2 different time scales in this system. And the idea is to use that for a neural network, where the fast spins are the neurons and the slow spins are the synapses. Right? So we can link up this, so we think of this as 2 fast spins, and they're connected here, and if we have 3-point connections with this slow spin, if this slow spin is changing state, it's effectively changing the interaction between these two. And this way we can get on-chip learning. So we're very excited about that. And I'm modeling this at the moment. And one way to model this is to have a stochastic dynamics where you have a self-coupling. If the self-coupling is small, the spin flips very fast. If the self-coupling is big, it stays in a long time in the same state. So here you see 2 neurons, 2 spins. One is with self-coupling 0, it's flipping all the time, and the other one has a positive self-coupling, it's doing that, right? Now what comes out is that the equilibrium behavior of this system can be mapped on a quantum system. So it can be actually equal to the ground state of a quantum system. And so if there is this local field which is happening in the dynamics is derived from an energy, which is basically the condition of detail balance, then you can write a Hamiltonian which consists of a classical Hamiltonian, which is diagonal on a computational basis, and a transverse field, such that the ground state of the system is related to this probability distribution that you have to get in equilibrium. And you have an explicit expression for this ground state. And so we're working now on a system, so in the dynamical case, we have this Markov process that goes to this particular ground state, but we also have a quantum process that goes to the same ground state. And so we have access to that. So here we would have to compute things here, we would have to use classical Monte Carlo sampling. but we have an alternative to use this with a quantum, with a quantum approach. Now I think this has interesting implications because there is now something called quantum statistics happening in these classical systems, and they can be made useful, and I think it relates to some point in the discussion. So each spin in this system not just has it's a binary variable spin, it just not has a mean magnetization, it's a sigma z, but it also has a sigma x. And what is the interpretation of that in this classical system? So the total magnetization is mx squared plus mz squared, and y squared is 0 because it's a real system. And you can write the variance in this single spin, the 1 minus mz squared, the amount of variance in the spin, the amount it fluctuates. You can deform it in two terms, 1 minus m squared plus mx squared. And you can show, so this spin, this one spin is flipping. If it is unconnected to any other spin, then m is 1, and it's just this term. If it is connected to the other one, then you see a decomposition of the total variance in terms of something that is coming from the others, how much is it kicked by the other spins, and how much is it doing its own thing, right? So you get a decomposition. This is the example of one spin, but you can also do this for larger spins. So I think this is interesting for systems that want to think about themselves, because, you know, I mean, here you get, so how much of my movement is due to myself and how much is due to the so that's just tip of the iceberg, but okay, I have not much time left. Let me conclude. So I have tried to tell you about consciousness as a dialogue of two realities, and it requires at least a probabilistic approach. For the atomic Boltzmann machine, there's a separation of time scales, and we can model that through self-coupling, and the equilibrium is equivalent to a quantum ground state. And there's an interesting link between probabilities and quantum models. So one is that I mentioned is that I can use quantum computing as an alternative for Monte Carlo sampling, which is something that I'm very much pursuing, which I think is technically interesting. And the second point is that these quantum statistics can say more about modeling of also purely classical systems. So here I end with the thing that I started with. If you use the tools of classical physics to understand the brain, you end up with a mechanical device, like a sort of AI clockwork. And for consciousness, we need more, maybe quantum. And I end with a quote of Feynman. So I very much liked what Demis was saying also, that I think it's very much important to have a bottom-up approach, where if we expand the toolbox, we can do more things, we can understand more things, we can build more things, and that will help our understanding of all the things that we would like to understand. Thank you very much for your attention.
And as I think we can all see, there's a lot more here from Bert. I encourage everybody to take time today to keep talking about it, and remember that I'm hoping that none of us disappear, even though we will be moving on to different locations, and hopefully these conversations are the beginning of many to come. But if there are any questions, I think we have a little bit of time. If there's anything that people would like to know. Anything that anyone wants to know now, or want to pick it up later? Mercifully, Bert, you will be grilled by me tonight.
Okay,
so thank you so much.
Okay.
This is very interesting. So basically, I don't know, ask it now because we don't. They usually saying that we're the difference between the map versus the landscape. Right? That we make a landscape, we perceive a landscape, and then we make a mask. The mask all that's different. That's actually what we're becoming.
on the topic of getting Roman trajectories from remember we it's not surprising. And I thought, now I know it's not
There's something that I didn't show. I would really like to get your attention to, which is, I did not have time to go.
Marco, are you ready?
There is this.
I will try to be lossless.
Try to be. All right, folks. The merciless march goes on.
I would like to just
And Bert and Basil will park you in the sidelines there. And remember, remember, supper is coming. It's gonna be amazing. And I think as I overheard you say that we will have a little bit of wine involved, which often helps. So I think that we will find a sort of a
Mexican hat.
if you find a Mexican hat, I mean, I would suggest you wear it. All right, so I'm going to hand it over to Marco Manca, and thank you for being here, Marco.
No, thank you. So, let me apologize in advance because after all the stimulation of the past 2 days, I'm not sure I will give you a coherent story, honestly, but I will try, in keeping with the spirit, to give you a piece of my mind about the matter. So, when I was invited to talk with you about mind and matter, my idea was to think, I'm a doctor, to think about the wetware behind it. And I like to start with the Egyptians because we are not the first one to reflect about the connection between mind and our body. And they had this very ingenious idea that the heart was the keeper of our mind. It's, in a certain sense, not even completely wrong, because there's in neuroscience a current thinking of embodiment that says there's a lot of information that gets elaborated peripherically in the body and that affects the way we think and act. So, long story of the brain, not necessarily to be read now since we are short on time, but let's say that at the times of Aristotle, the idea was that the brain would only be a device for cooling down the heart, that was the site of the spirit, and only in the 17th century with Thomas Willis, we started figuring out that the brain was actually having a function, and this function was not correlated to the ventricles and the circulation of some sort of spirits. Another extremely important thing about the history of our way of thinking, probably even today, about the brain, is that thinking of our mind and its embodiment, we have always been thinking to the highest technology that was available to us. This is fairly important because even when we observe reality, we tend to collect pieces that are fitting with our model, and we tend to get trapped. Now, this is an example from neuroscience. Imagine that this model of the way we think about how our encephalon connects with our spirit is known to be wrong, but what we try to do with mapping functions, specific functions on pieces of the cortex, is very much similar to this, and we know it's wrong. Now, this is just a very little example, again to the heart, because the heart is one of the organs I think we know the best. It's big, it's clear, it's easy to study. Until 1950s around, we had a model of the heart that described the ventricles, which are the most essential part, as formed by a common muscle and a proper muscle of the two ventricles. And this had huge implications in the way we thought about heart failure, in the way we thought about a lot of the reality we measure in the clinics. Now, the interesting thing is that's wrong, okay? And that's wrong for something that is as big and whose function is as clear as the heart, okay? In reality, the heart is formed the way it is by torsion. In fact, this also makes a lot of sense with embryological development, because it starts as a tube, and by torsion it gets to the shape it has. And in order to fit the model we had to the embryology, we needed to invent and pretend that we were seeing in histology a lot of processes of digestion and production of new pieces so that we would fit this part here. And until the 90s, the model was not known because it was, the new model was not known because it was described by a Serbian scientist. And we were still trying to cure terminal heart failure, as instance, by wrapping around the heart a piece of deltoid that was cardiized, so that we had the idea it would help pushing, pumping the heart. Now, what's the impressive trick? Galeno had already described that if you were observing the, sorry for touching the microphone, if you were observing the vein in the brain, you would see a motion of suction. This motion of suction could not be explained by the model we had, so we were actively teaching medical students, I was taught the same, that in reality there was no suction at all and it was a passive feeling. Consider it's really the stick, the muscle in the ventricle. It was a passive feeling with just 3 to 4 millimeters of mercury of pressure differential. In reality, because of this form, the heart really has a torsion around its axis and it sucks blood. It doesn't only pumps. Now, why this is important? Because we tend to take a lot of things for granted, also about the brain, of course. And so, this was the reason why the next slides are here, although they will look like some might refer to things that have been said. As instance, it's completely common thinking that we have 85 billion neurons and that we have around 10 folds as many glia in the brain. These numbers don't check if we go and verify. We have 120 billions of neurons. 100 of these are in the cerebellum, and we have just around 4 folds the glia. And okay, this also happens for a number of functions that we attribute to it. Classically, cerebellum is thought of not affecting personality and thinking. This is because the way it affects personality is extremely tricky to capture in the clinics, but for decades, relatives of patients with cerebellar infarction were describing changes in the personality and the thought process of their relatives. And in fact, around the 90s, I don't know how to pronounce him, sorry, first proposed that it's true, the cerebellum has functions that are above the function of the cortex for thinking, and in this instance, the cortex works as an accelerator and it learns stuff within the manifold it has already, so it optimizes stuff. But when we are trying to learn completely new tasks or objects, there's an heavy involvement of the cerebellum. Now, I love how the McCulloch and Pitt's idea from the 40s have become the terrific tool monster that Demis has described. But my problem with all these advances is that it's a fantastic tool, but I'm never completely sure how much it really tells us what happens in the brain. It tells us there's a very interesting model that applies to a lot of stuff that we thought were unique, but does it really work well for the wetware? And this is an example. I mean, they tried to study the layer 5 cortical pyramidal cells that were mentioned already before, and it takes several layers of DNN just to capture the I/O dynamics without having any other ideas about what's happening. And I want to stress, I/O dynamics is not everything a neuron does, of course, right? Because this is the short-term dynamics of the neuron, but then the neuron in his life does a lot of other stuff, and there's a lot more complexity happening that is not captured here. And this has important implication because I don't know how much alpha 0 consumes, but we for thinking consume very little energy. In fact, I spent all my COVID lockdown thinking, and I still need to go to the gym. So there must be something in the brain that is happening that allows us to learn as instance to distinguish an object in a picture when we are 9 months old. Okay, and I understand why Minsky thought he could do it with a couple of PhD students, undergrad, whatever, during summer. But okay, there must be something behind it, so the question really is, what is our wetware made of? And when you are in the clinics, our brain is not really just the neurons, right? It's actually the second killer worldwide is the vessels that are in the brain. And again, because we have a lot of preconceptions, for decades we have been teaching medical students that the polygon of Willis at the base of the brain is responsible for completely linearizing blood flow that arrives from the body to the brain, so that the brain works in completely constant flow, laminar flow conditions. And in reality, we know now from magnetic resonance imaging and other tests that blood flow actually pulsates. It makes the brain move due to the hydraulic pressure, and there have been patients described where, as instance, epilepsy is triggered by the pulse, which, if it was completely laminar, would not have been possible. And another extremely important thing is the immune cells, the glia and the immune cells in the brain. In fact, this is work very close to his home. Again, they have recently analyzed in depth 1 cubic millimeter of brain, and they have described a lot of relationships between cells and neurons. Within the brain there's different types of glia. There's microglia that's belonging to the immune system. There are a lot of microanatomical structures that we didn't even know existed. And why is it important? So I really loved when Joseph, I'm sorry that he's no longer here, mentioned non-compactness yesterday. Because so qualitatively, with the poor language that doctors have, there's a discipline that is emerging that is called biosemiotics. And the idea is molecules and interactions within the brain are not messages. They are not univocally meaning something. And as instance, within the brain there are very large molecules that are called major histocompatibility complex 1 that are normally used to present antigens to the immune cells. And in the brain, they are also mediating a functional conversation between glial cells and neurons. Glial cells are also excitatory cells, even though they are less well described than neurons. And they regulate learning in a lot of ways. For instance, myelinization is an activity that is not governed by the neuron, but is decided by the glia that decides to wrap around the neuron or to unwrap. Okay, and there's a lot of interesting mixing in this space. For instance, the team by Mario Capecchi described this extremely interesting model. It was the first time that they had described a situation in which an animal model of obsessive-compulsive behavior could be rescued, not by an intervention on the brain, but by bone marrow transplantation. And then the change of the consequent change in the long term of the population of microglia in the brain changed completely the disease, the mental disease of the mouse. And there's a lot of cases. There's this team in Turkey that is studying a family that has a congenital genetic defect of this of the receptor for a transporter of cholesterol, and they never develop bipedal motion during their life. And we have no idea why, clearly. But it's lipid disorder that transforms into a, how to say it, always identical neurological conditions. And within the brain there's a lot of these pleiotropic effects that have potential importance to the way we deal with information, that could contribute to justify both why we are very low energy consumption and why we are so efficient that Professor Houdin could completely confuse my mind with yesterday. Now, why do I love this? Because when I met Jussi, essentially I had always thought of all of these through the lens of the systems dynamic. And of course, it's fascinating to think that rather than having just the manifolds of behavior that would emerge from a neural network, now there's a lot of other systems that are all optimizing for completely different functions and signals that are contributing to the emergence of patterns that we would have never explained with just the neurons. And then meeting him, his tool, his model, could justify that there's also other tools of computation that are actually sustained by just the competition that we had to do during evolution. Often when we think of the human evolution, we just imagine that we needed to feed and escape from a predator. But a huge role in how all of this mess has evolved is parasites and infections that have potentially nothing to do with growing in intelligence. We have no benefit of becoming more intelligent from, to defend from a parasite. Nevertheless, a lot of the tools our neurons use for communicating, the exchange of vesicles, these are all residuals of our fight against viruses and other parasites. And this has become the substrate for the emergence of some dynamics that probably were completely unexpected in the general design of evolution. Okay, and then I will keep it super short, sorry. Oh, you told me to shorten and I shortened it.
I thank you for more than one reason. Hey,
have I been too short?
No, it's fantastic. Thank you very much. Any questions for Marco?
Well, I could make a comment.
Yes.
Because Carl Freebrand always told me it's not the neurons, it's the dendrite cells and their combination in the glia that is the important thing for information processing.
So both are extremely important. Probably they exchange weight or importance also depending on the time frame at which you are looking. So neurons are protagonists for sure of the instantaneous short-term reactions. But clearly there's a lot of other cells and dynamics that play roles in long term.
Anyone else? Any questions, comments? Oh, sorry, I couldn't.
Yeah. For me, it was too short perhaps because I didn't quite understand the connection you wanted to make between compactness and glial cells. That seems like a big leap to me, so I'd like to hear more about it.
Probably I skipped something. So it was not so much about the glial, but about the fact that these cells are all communicating, sharing messages that are not again, the word that doesn't come to my mind, univocous. So in a communication between finite state machines, if I send you a message, it's clear that it will mean the same for you. And until now, I had always referred this to Wittgenstein emergence of meaning, negotiation of meanings. But if I understood right, and I admit, as I told Joseph, I still have to read the literature I downloaded because it was the first time I heard about compactness. His point was that non-compactness injects this ambiguity in a formal way, though. Am I wrong in what I understood? You can correct me.
Well,
I heard yesterday about non-compactness.
As far as I understand, compactness is the property of all finite subsets. If there's a model for the set, then if compactness is true, there's a model for each of the finite subsets in the. Oh, sorry.
Yeah.
Right.
So if it's compact, it can't. If it's
so
not
if
compact,
there is a model for each of the finite subsets of a set, then there is a model for the set. And I wasn't sure how that fits in with ambiguity. I know Joseph saw these important connections. He's got the diagram back there about what compactness means for our understanding of the mind in the relation to computation. But anyway, maybe it's a question for him, not for you. So.
I hope to read enough to be able to answer next time. But from yesterday, I really didn't.
Sorry, carry on, please. More questions? Anything? Anyone?
Just a quick comment.
Demis,
I agree with you, by the way, that I was not, just to clarify what I was saying, is I don't think the deep learning models necessarily tell us very much at all about the brain. It's the inspiration is more the other way around, which is at a higher systems level, things like reinforcement learning or what is the episode, do you need episodic memory, that's where we get inspiration from the brain, but it's quite loose. So I wouldn't recommend something like the Blue Brain project where you try to really, take it literally, right? I think there's no reason to believe in silico and in carbon systems are going to do it in the same way. So there's a limitation. I think it's high level the inspiration both ways, not to the real. You can't use the deep learning systems to really understand fully the brain mechanisms.
We are on the same boat.
Yeah,
I knew in reality.
Yes, and of course the brain is much more efficient in terms of energy usage, but as AI designers, we're interested mostly in overall performance. Even if it uses a lot more energy, right? Data center, it's okay. So, yeah.
Oh, anyone? Anything else for Marco? All right. So thank you, Marco. Thank you, everyone, for your questions. And next we have Martti, Vainio. And I think while we get Martti set up, if anyone needs to use the facilities, this is a good moment for that. But
we're actually ahead of schedule now.
We are a little bit ahead now, miraculously. I don't know. I over-bullied Marco by accident, I think. But luckily, we know each other very well. So no, and really, hey, all sort of joking aside, really the whole idea was to try to get everybody here to see if there's more to talk about. This is definitely, I'm hoping, not the last time we're going to meet each other, right? And not always all together, right? If there are interesting ideas, let's try to connect each other with them. If someone has resources to do an experiment that needs doing, let's try to do it. If someone has theoretical ideas or mathematical tools, let's go for it. This is the beginning rather than the end, so to speak. So, in that spirit. All right, Martti, give Mill about for a minute, and I will get the rest of the gang back.
No problem.
Back in.
Shake my neurons up again.
got the guy more or less here.
Yes, exactly.
So, Martti, I think it's time to kick it off. We have, I see Marilu is gravitating in this direction, so Martti, take it away.
Thank you. Martti Vainio, I'm a professor of phonetics, a speech scientist. That I've done all kinds of stuff with speech, including teaching machines to speak for a while. But this speech talk will be sort of a bit inspired by the theme of consciousness, in terms that speech is the most common sort of meaning moving mechanism that we have as humans. We've been speaking here for 2 days, and I don't know, hundreds of thousands of words, maybe at least tens of thousands of words we have sort of received in our ears and then also produced. And all of those words, each one of them is a symbol that basically is an arbitrary form that refers to some non-arbitrary thing in the outside world that is common for us. And some of those things are very abstract, and some of them are concrete. And then I've heard at least 2 times here in some speeches that we feel the meaning. Now, what would that mean, to feel the meaning? That would be sort of referring to the conscious experience of meaning. So what is meaning? It's, I guess, the interesting question. And where does it come from? What is the meaning of meaning? So, logos. Logos is Greek, meaning speech, or word, or whatever. It's been used for, and pro is before. So, Peirce was a semiotician, I guess, the sort of founding father. So he talks about things called semiosis, which is any form or activity, conduct or process that involves signs, including the production of meaning. And semiosis, if you think about semantics, they have the same root. Then there's another semiotician who says that semiosis is the criterial attribute of life, what that might mean. He also said culture, so-called, is implanted in nature, and the environment, or the semioticians talk about the Umwelt, is a model generated by the organism. And semiosis, the meaning-making process, is something that links culture and nature and us, our organism, with the world, the environment. So it's something that we use for. So that's what this process of semiosis is. Then we have evolution. And why I need to talk about evolution is because speaking is a product of evolution. We learned to speak. Some say that even 1 million years ago, but the sort of current opinion that I subscribe to says that we've been speaking at least 500,000 years. That's a while. As opposed to the fact that we've been writing and developing mathematics for 5,000 years or so, in a sense. So evolution, John Maynard Smith, I have a link there they wrote a book with this Eers Marie Mari, I don't know how to pronounce that name. It's a Hungarian name, although I'm a Finnish speaker, and Hungarian is a language related to Finnish, but totally different in those sort of sound-based way. So, if you think about sort of our origin, the first big important transition, if that can be called a transition, is that the universe became from somewhere. So we had a big bang, and the Earth formed 4 billion years ago. Then we had life, and this is what Maynard Smith talks about. These major transitions in the evolution of life itself is that we have chromosomes that you have these independently replicating nucleic acids and eukaryotes and sex and all these, and then you have multicellular organisms, and then you have social groups. And those social groups, then he says that the last major transition in the evolution of life is language. Because language allows for cultural evolution. So now we have two different things evolving instead of just a natural sort of selection-based biological evolution, but we have also the cultural evolution, which is, of course, provided for us by language. And because language, like genes, is a replicator of information, we can take information, replicate it, and through learning, we can create culture by transmitting that information over generations. So it replicates symbolic arbitrary information. But at the same time, the system, language, itself is a culturally transmitted system. It's as if an organism on its own, living sort of in the society, independent of the individual. So we have these two systems now. And it has to be acquired by the individual, the system. And we all learn to speak automatically as children. Nobody has to teach us. So it's a natural thing for us to start speaking. Well, this is just why speech is interesting, because studying speech, you can start from the physics, the acoustics of the vocal tract. I've littered this with pictures from studies where I've been contributing, and these are the ones. But yeah, so you can go from physics to physiology and anatomy and sort of cognitive neuroscience and slowly towards language and linguistic structure and then how separate languages are evolving, and all the way to art and philosophy, maybe even theology. And so we have some sort of a continuum there between all kinds of ways that we can, and all kinds of sort of contexts where studying speech is very, very relevant. So we have this epistemic chain, and sort of in epistemic chain that potentially allows for linking natural sciences and humanities in a sort of fruitful way. And yeah. Now, what is the speech signal then like? Here we actually have was basically a scaleogram of speech. It's a bit like a spectrogram, sort of done using the Fourier transform, but instead of Fourier transform, we use the continuous wavelet transform, which produces this sort of scale space. So it sort of unfolds the one-dimensional signal into sort of many sort of frequencies that are in this sort of scale space. And for some reason, nobody had done that before we did. But it's extremely revealing because maybe I'll go forward and then go back. This is another study where we with a few mathematicians, for some reason, I got them excited about speech and they wanted to produce a model of the vocal tract using these sort of finite element methods and then use the wave function and Navier-Stokes things to find the resonances in the vocal tract. Because these resonances in the vocal tract are extremely important. They are, if you think of sounds in general, when you describe a sound, all sounds can be described by 4 different sort of features. They have some sort of a length, they have sort of amplitude in a sense, sort of fluctuating, or energy or intensity that we hear as loudness, and then they have, typically if they are sort of some sort of periodic like sounds, they have a frequency and a harmonic structure, and then they have complexity, a timbre. But so you have 4 degrees of freedom for analyzing and manipulating sound. But in speech you have a 5th one, because one of the really important features in speech, and because you have an extra degree of freedom, it allows for much more efficient coding of information. And that is what is called a formant structure, which are the repercussions of the resonances in the vocal tract when we push sound pulses through it. We just do that. I do it in general 100 times a second. I produce a pulse of air, and it sort of resonates back and forth in my mouth, and a little bit of it escapes my mouth as the sound that you hear. But basically, it's we wanted to see many things, but one of the things we wanted to. This is a very, very old way of phoneticians to depict vowels as sort of categories based on how the tongue is positioned. And Panini in India over 2,000 years ago, they already had this type of a sort of system because they wanted to learn the poetry by heart, so they studied language sort of a bit more objectively than we did here. So here's a spectrum of a vowel E, and those what we call formants, the resonances, can be seen as these peaks in the envelope of the spectrum. So they're important because from there we can infer where the tongue is. Well, when we hear speech, when I say E, all of you immediately know that my tongue is in the front of my mouth. Because you can't really produce the E yourself differently. So we're connected in this sort of coding way through our anatomy and physiology. So if we go back to the speech, we can see that these are sort of pseudo frequencies because they are in this wavelet analysis. There's really no frequency. There's just the length of the little function that the Mexican hat. But this is a complex Mexican hat because the signal fluctuates around 0. So you need the phase as well. So so you can see that here's very high. There's some energy here, and it's an S. And then you can see these resonance structures that the lower you go, you start seeing the sort of harmonics. And this is the lowest harmonic is the fundamental. It's how my vocal folds are vibrating, the frequency of the vocal fold vibration. And it changes and produces a melody. And this melody is independent of how my tongue has been moving around, producing these speech sounds, a sequence of speech sounds. But then, sort of when we go down, sort of to lower scales, we get this interesting hierarchical structure, where we can see that there's some sort of as if scale invariant structures in the speech, and these are now representing the energy envelope of the signal. So we code things, the speech sounds in the movements of the vocal tract. We code the speech melody by modulating the vibrating frequency of the fundamental, which excites the vocal tract and produces sound in general. But then all on top of that, we modulate the energy distribution in a hierarchical manner, so that we get these at this point sort of 32 hertz. There's already sort of acoustic events happening. Speech is extremely fast. So that 32 hertz you should be able to hear as a tone, really low, but we don't. So, but if you look at the sort of 4 hertz and 1 hertz, which is of course 1 second, you still have these structures, and these structures are arcing in a sense that you have a beginning and an end. So we are sort of hoping, we haven't shown it, I don't know how we could show that sort of perceiving speech, or the auditory sort of analysis that we do in general would be something like this sort of scale invariant scale space analysis that we do here, because that gives us this spatial sort of spatial representation, as if or of the temporal structure, because you connect those. So these things are then sort of temporal events, but we can identify them in time, and this way go back in time, in a sense that, oh, this event, because there's this sort of a form of a sort of envelope at this frequency or this wavelength, actually means that this unit started then. So we have, for that we can sort of take all of those, the sort of features that the visual system uses for sort of recognizing features in the visual field that might be the same features recognizing features in the auditory signal, which is a temporal signal. So that's why it sort of feels quite interesting and relevant to unfold them, because this is a hugely redundant signal. It produces like hundreds of copies of it, but at different sort of levels of analysis. Okay, now to sound symbolism. Now you know what speaking is quite quickly. I hope you're quick learners, because I'm sure that who knew anything of that? Yeah, few people. Very few. Things that should be learned in school, I think. Okay, sound symbolism. We have shapes, different shapes. And I won't even ask you which one is buba and which one is kiki. No use asking. So sound symbolism is what is typically called iconicity in a sense that there's some absolute direct imitation of the thing that the sound that we produce refers, like onomatopoeia. The name of the bird cuckoo is sort of very similar to what the bird makes as a sound. Then we have sort of relative, we have ideophones, like Japanese goro, I think is to go, just to go, and goro is to go faster. Yeah. So we have these ways of signaling, sort of fairly directly referring with sound to the object. So this is an old one. This sound symbolism has been sort of Socrates, or Plato, I guess, from Cratylus onwards already sort of found this as an interesting problem. So we have sort of from 98 years ago, somebody realized that you can call these two things mil and mal, and people will pretty consistently tell you which one is mil and which one is mal. I wouldn't even ask you that. And this is the kikibuba. It was originally Sapir who did it in 29, but he called them takete and maluma, which is a bit more. It's a different kind of, as opposed to kiki and buba. But if I ask you which one is ah and which one is e, now I'll ask you which one is e. This kiki, yeah, e, and this is yeah, with ah. If you just needed to, those just simple vowels. What is in? There's nothing acoustically like that in E. There's nothing in acoustics that sort of is related to those shapes. So what might that be? Why are we sort of experiencing them in an obviously sort of consistent fashion? So we've been working on this sound action symbolism, sort of trying to look at the sort of this sort of a multisensory motor links between the body, especially the hands, and the articulatory apparatus in terms of how we might be sort of consistently be exploiting these this link. If there's a systematic link, it's an interesting. So first thing we did, we asked people to react to some color randomly, like green, but ask them to do either grasp, sort of press a sort of sensor like this, or between their fingers, because those are the two basic things that we have in our hands, sort of really canonical gestures of hand gestures, or is this pinching gesture and this grasping power grasp, it's called even. So we had this sort of interactions, this reaction times, this very simple experiment where if it's E, people react really fast with their sort of pinching gesture, and if it's with this sort of power grasp, and the other way around. But then we ask them to listen to speech, and when they hear, when the color changes, they were all it was pretty much the same. So it was also in listening, and and we did one where we measured the sort of premotor thing. So it's in premotor thing, it's in perception, it's in production. It was sort of very consistent. Then one of the experiments we did was we showed pictures of people grasping things, and we had the same results. The E is always sort of associated quickly in the motor system with this sort of precision. Yes. So we had tools sort of also, and those tools also sort of evoke this effect. So this is very much in line with what's called embodied cognition or enactivism, in a sense that our cognition is based on our relationship with the environment, with the sort of affordances in the environment. The small things afford for grasping with your fingers, and bigger things. So you have this magnitude thing. Why mil is small is because it as if in this sort of multisensory and cross-modal sense, it's associated with what we do with our hands with respect to the size of the things and so forth. So that. And then we're interested in space as well, because these are basically spatial relations with size. And we wanted to look at pointing as if towards your body or away from your body. And we did it with both the hand and the foot. And there we found as well that E, being a front vowel, is associated with the forward movement, and back vowel with the backward movement, and with the foot as well. So those vowels now, E and which are sort of really basic vowels. All languages, I think, have E and If the language has 3 vowels, like some Arabic language, those are the vowels they have, plus maybe some third one. The E and I think are pretty much in all languages. So, not all, but in some sense, a front and back, or open and so forth. So there's an interesting thing going on with respect to this. It's an empty. empty one. Okay. So obviously we are sort of linked to in speech and our sort of coding in this non-arbitrary way to the physical world through this sort of loop between that links our articulatory organs and our rest of our body. So purely this sort of basic inactivist view. So one thing that this is very preliminary, and I don't really believe the results because I don't believe in fMRI at all. But what we did was when you look at this this scale space sort of hierarchy, which is this way now, you can do a sort of a spectrum of that, or just average out and see how in particular speech signal these events, sort of these very slow events are distributed in time. So typically you have like there's a lot of sort of pulsing around at the syllabic level, 300 milliseconds or so, which is and then you have another levels, but sort of phrasal level and so forth, and these sort of spectra or what do we call the profiles for what we call speech prosody, the stress and boundary sort of chunking that you can see there are a bit sort of language dependent, and so we've actually compared languages and compared language learning with this tool. This paper actually comes from picture comes from this language learning. So we had a story. Somebody had written and read a story for 8-minute long story. So meaningful story, and we had another version of it. Somebody sort of transcribed the story and then just scrambled the speech sounds so that it, and then they read it again, so it was sort of mimicked the original speech, but with different sounds, so that it was as if speech non-Finnish speaker wouldn't probably even notice that the other one is Finnish and the other one is nonsense. So there's no meaning in the other one, but it sounds exactly like there was meaning. So we put that stuff in people in fMRI, and then we looked at those spectra from those scale space analyses, and at different levels of sort of frequency or time, and we found that if you look at the phrase density, and this is the gibberish speech and comprehensible speech, they look pretty much the same. There's not much difference in the sort of brain response, and at the syllable density, and we can sort of we can expect that at the syllable level we are really tuned to the articulatory sort of motor side of the speech. And so, quite interestingly, the motor cortex is activated when there's meaning, but it's not activated when it's gibberish. So this is the only thing I'll take away from this, is that that's worth looking forward sort of again, because it means that, for me, logically, it says that meaning in speech, and that would be language in general, is mediated by the motor system. So, yeah. Do I have time?
We have a little bit more time, yeah.
Maybe I'll Oh, I had some synthesis because we used some deep mind methods we did this analysis and maybe.
Martti think like less than 5 minutes.
Yeah. There's no sound. There's no sound. So yeah. They sounded good, but there was some point that I wanted to make. But yeah, I'll stop here.
Yeah, thank you very much. Any questions for Martti from anyone?
This seems to be the other half of the story. Hear it. That play part of this.
Yeah, there was another part. Yeah.
And how we hear, how we filter sound, how we understand speech. Don't you have to have an understanding of the ear, like how the ear hears?
Yeah. We've studied that. We've looked at how these sort of particular features, so temporal and frequency and intensity features, are sort of processed at the sort of very early in the brainstem level, and we've seen that at that level, time, frequency, and intensity get already mixed in a sort of predictable way that is actually modulated by the language. The Finns are different from Germans and English speakers, and we would be different from Chinese in terms, because the language treats these features sort of in this trade-off sense.
I think Marilu was there a little bit before you, Paavo, so Marilu and then Paavo.
Okay, Martti already knows what I'm going to ask. So speech comes first, right?
Yeah,
With
it
respect to any other
did
kind
come
of
first, for at least.
Of any other kind of symbolic system.
Yeah.
You showed that.
Yeah, but I didn't have time because I had slides of how those symbols actually arise.
Okay. So I mean, this is what you
Yeah.
thought.
I'll tell you a story instead of the slides. My son, he was a bit slow in learning to speak, but he was intensively into toy cars, and he would go like, make the car sound. And then he started pointing at the cars and go. And he would point toy cars, real cars and everything. Oh, he points so and he makes that sound. So he refers with that sound to car in general, not just particular toy, but the car, the concept, in a sense. So next he started saying, and he stopped pointing. And at that point I didn't realize that. He just adds another syllable because Finnish words are disyllabic. He just, from the Indian environment, he took the most common syllable and added that to the sound. But then we looked at that T is actually pointing with your tongue from your body. So that pointing gesture became abstract. And then you had this sort of iconic reference of the sound source. And then he started, before he still pointed, he also pointed to airplanes and he said, and those became and so they and then you didn't have to see him anymore. And when he said, you knew that he meant the car and probably wanted to find the toy car. So he could refer to an absent thing with this disyllabic gesture sequence, where the other one is the referent and the other one is the function. So, hey, this is interesting, and then we found out those links to spatial signaling. So, oh man, it wasn't the ambient, it was, and And then ha, that's why the P as a syllable is the most common syllable in the world, because it's still there as this sort of a gesture. And so I thought that, can I imagine a more plausible way of how words and symbols and abstraction and categories first came into this world?
Yeah, but indeed, I mean, it's still not clear to me how we can rule out the fact that in another civilization, for example, we can, I don't know.
No, languages. Once you have language, once you have this as if abstract symbol, you can then start. Oh, we can invent more of them, and then you can start ordering them around, and suddenly you have syntax. So means different from you can have, and there's a sort of natural way of looking at agency and stuff like that. So object and subject and these emerge quite naturally, I think. So this way you have this complicated system emerges from these little pieces. But the emergence relies on the fact that there was this sound symbolic link in the beginning, and this I claim that this sound symbolic link is always there, and it's still there, and it's the way that we learn to speak. It's the way that how we learn to feel the meaning of these abstract, arbitrary symbols, because they're not all the way down abstract.
Paavo, I think you have something.
Yeah, how are we doing with time? Is it still okay?
We're okay. We got a little bit of time.
So anyway, I think it's kind of tempting to say that our thinking is like inner speech, and I know that from my experience, because I was once working in the Stockholm University Library, and I was writing, and the guy next to me say, "Can you think quietly? Kan du tänka tyst?" Meaning I was actually speaking while I was writing, so it was like motor. But I was thinking of the experiment you showed, that where we do get activation in the motor cortex when it's meaningful. Does it mean that when I listen to you speak, that
that's a long theory of sort of motor theory of speech perception.
But in the sense that when I listen to you speak, is it so that activates my own motor speech?
Yeah.
So that I kind of speak.
Yeah. So that you as if speak the same thing. So you entrain to me in your motor system entrains, and that way, that is actually what they say. Some people that how you would understand this. So, because I can subscribe to that. And it's also, the motor system, remember, is linked also to all of your body. So these sort of spatial affordances and the space in general is always there.
Or anything else? Any other questions for Martti? All right, I have a finishing question, Martti, for you. Is that, and I realize in a way that I think one of the things that's become clear over the last 2 days is that sort of the whole notion of consciousness is something that I think we all need to work on trying to define more and more sharply. But I would put it to you like this, that do you think this is sort of in the spirit of Demis, that is there any signal in speech that I think that to you sort of signifies something that's related to the issue of consciousness? Or is there something that...
I would say that because we feel, we experience the meanings. If the conscious, sort of, if you think of consciously trying to listen to me and what I do, you basically hear the sound structure. You categorize the sounds that I do sort of sloppily. You have this sort of idealized sort of phonological, as if perception of what I do. But you don't have access directly, conscious access to the meaning. in the sense that you would analyze the meaning, you feel it, don't you? I mean, I've been sort of trying to analyze my consciousness in answer, but so what that entails, in my opinion, is that feeling then is our comprehension, the understanding of the meaning is that feeling, that experience. And if it goes through this sort of a link, sort of embodied link to the environment, then consciousness and artificial consciousness, in my opinion, needs the environment. Yeah.
All right. You?
You must have done studies with people who were born deaf and then got a cochlear implant. So they learn.
I forgot to say, all these things sort of go also with sort of sign language. It's not sort of.
No, but what I'm wondering, if someone suddenly is able to hear much late, at the age of 2 or 3, so there's been a lot more brain development. Do they then learn language differently?
I'm not sure, but if you don't learn it until some critical period, typically it's later. Then you don't. But yeah, you might imagine that there might be some, but they will probably catch up quite quickly at that age, really quick.
I think the interesting thing though is, how did they learn it differently? Because in a way, if I learned to be a Turing machine before I learned to speak, maybe I'd simulate speech, kind of thing. And I think in a way, that's
would I treat you as a robot then?
That's right. Yeah. That's the big question. But hey, Martti, thank you very much. Thank you everybody for the questions. Powering on, Ron Chrisley. I've been told he's a great closer. He's gonna, apart from sharing us his brilliant ideas, which are manifold, I also hear that he will synthesize it all to us, so that when me and Paavo and Sabrina speak about what happened here, it will take all of 5 minutes, and we'll really be mirroring what Ron said. So
I think I'm going to let you down.
Ron, no pressure, but we need a strong finish here, mate.
I think I can provide a strong finish, but I'm not sure if it will be a summarizing one.
Thank you, Ron.
Thanks. Okay. Great. Okay.
Oh, I think we.
Oh,
yeah.
It was there. I'm unplugging by myself, I guess.
It looks like it's waking up now. There you go.
Okay.
That's it.
You can see it from here. Is that okay?
I'll just use this screen.
Okay.
That's right.
You don't have any notes on the presentation?
What?
That's cool.
I think it'll work. Thanks. And yeah, thank you for, well, not just to the organizers at UC and Paavo, but also to all of you for staying till the end. Maybe I have a captive audience here. That's great. This is not really a good title for my talk anymore because I've decided to focus on one particular issue, which really doesn't have much to do with quantum mind, although I will mention quantum computation a couple times. But what I decided to do in reorganizing my talk was I decided to take UC's injunction seriously, and I wanted to give you an idea of the kinds of things I'm interested in for the purposes of you knowing me better and maybe planting some seeds for possible future collaboration. So the first slide after this one reflects not just my love of paradox, but also is trying to basically address UC's injunction, but also let me get on with one particular topic. So really what I'm going to, this is what I'm not going to talk about. And it's a list of things that I want you to know that I'm interested in, but I'm not going to talk about any further. So one thing, I'm not going to read out all these lines even. I guess you can't see them too well. Maybe I can zoom in. Well, I think I'll just, yeah, what's that?
Maybe read them.
Okay, maybe read them, but I don't want to waste too much time. So one thing I'm interested in doing is understanding the non-conceptual aspects of mind. And I'm interested in figuring out how we can specify those difficult, those contents are difficult to specify linguistically. So how can we use technologies and non-linguistic methods to specify the way that we experience the world before language and independent of rationality and systematicity, for example. I also would like, one of the things I'm interested in is looking at, for example, Sir Roger's chess example as a constructive challenge for contemporary AI, contemporary machine learning, rather than a demonstration of AI's impossibility. So taking it seriously and looking at metacognitive machine learning systems and creative machine learning systems and algorithms for creativity in machine learning. Way back in 1995, I introduced, maybe this is, well, as far as I can tell, there were only two of us who wrote, there were two of us who wrote in the same year independently papers on quantum neural networks, and there's this weird notion of a Bohmian quantum neural network. I don't think that's a good name for them anymore, but they're very different from what quantum neural networks are understood as nowadays. But I'm interested in talking to people about whether there's some different way of seeing the advantages of quantum implementations of neural networks. I'm also interested in, here's another gesture towards quantum mechanics. I'm interested in using the formalism of quantum mechanics, or related formalisms, superpositional formalisms, to capture indeterminacies of expectation-based models of sensory motor experience. So it's very similar to the predictive processing models that are popular now. If you understand the contents of experience as being expectations about what inputs one might receive under certain, if one performs certain actions, then you get certain kinds of indeterminacies. There's more than one way to, say, move your gaze to a particular point of to a particular fixation point, and because there are multiple ways, there could be different predictions about what you might see were you to make those different moves. Those indeterminacies might be best represented using superposition. So that's something I'd like to explore and talk to people about. I've recently presented a defense of physicalism against a famous philosophical argument against physicalism. It's the knowledge argument. It's the one that involves Mary, the neuroscientist who's never seen color, if you know that. And I did that by constructing a self-referential physical fact that I proved cannot be known by Mary before she experiences seeing red for the first time, but can be known by her afterwards. Therefore, it's basically a constructive response to Jackson's argument. I've also been writing things about how one can be a physicalist without being a qualia eliminativist. So having my cake and eating it by being a physicalist who nevertheless doesn't have to be like Dan Dennett saying there isn't any such thing as consciousness, right? So trying to say that we can recognize qualia as existing, it's just that we're radically wrong about it. So not all false theories require the elimination of the things that they refer to. And so my position is that whether qualia exist is an as yet undecided empirical question. So the people who sit in their armchairs and say qualia definitely exists, I can tell by introspection, and the people who sit in their armchairs and say they definitely don't exist because it's incompatible with the physics, neither of them are correct. And an implication of that is that even if we turn out not to have qualia, it might be that we could construct artificial agents that do, which is, I think, a really perverse result, but I like that. So here's what I'm really going to talk about. I'm going to challenge this diagonal argument that has been presented, in particular by Sir Roger many years ago, against artificial consciousness, or even against behaving as if an artificial system behaving as if it has conscious understanding. So I want to defend the possibility of artificial consciousness. This argument is an excellent argument, the one I'm going to be attacking. It's excellent in that it's superior, say, to the Chinese room argument in at least a couple ways. It's mathematical, which I think is an advance. It's very precise and it's well thought out. But it's also very strong. It's not just against computational consciousness in the sense that Cyril was trying to say the Chinese room doesn't have any consciousness, doesn't understand, but it's more than that. It's actually saying not only, it's actually arguing against even the possibility of a computational simulation of conscious behavior. And I think that warrants attention. And I'm going to use Sir Roger's formulation from Shadows of the Mind, because it's exceptionally clear, it's rigorous, it's the most complete and rigorous statement of this argument that I found. And also because it's formulated in terms of computation rather than in terms of, say, proof, although Sir Roger does this too, but he expresses it in terms of computations at one point rather than expressing it in terms of, say, proof within a formal system and more the Turing formulation than the Gödelian formulation, I would say. And I think that makes it easier to see the connections, the application to artificial intelligence. So that's why I prefer that. Now, why? Why give another response to this argument? There have been many responses, and that's one of the great things about the presentation in Shadows of the Mind is that Sir Roger took the time to understand all the objections and then go through them and just refute them one by one, and he is successful. All the objections he considers, I think, he has a reasonable response to. So that's why I think we do need another, because he was so good at refuting all the attempted refutations. But I would say that my reply has an advantage in that I basically give him everything except what he wants. So I give him I even give him his conclusion G. Wow. I'm going to grant G, conclusion G, which is there is no knowably sound algorithm that mathematicians use when trying to ascertain the mathematical truth of statements about computations. But nevertheless, I'm going to show that it doesn't really give you, it doesn't really cause problems for artificial intelligence or the simulation of conscious behavior. Also, I think seeing why uncovers some interesting insights into computability and simulation. So here's my statement of the full context of the diagonal argument. The diagonal argument proper is really only number one, I guess. So number one says there are questions, for example, or specifically about computation that conscious humans can answer, but no computer can. And that's really what the diagonalization establishes. But there's another premise here. It follows from one that no computer can fully behave like or simulate a conscious human. I'm going to question that. And then the next premise is, but fully behaving like a conscious human is a requirement for being conscious, and I'm going to only spend one slide or two slides at the end questioning that. But the full argument therefore concludes that no computer can be conscious. But notice that we got there by saying that no computer could simulate conscious behavior, which is really a strong point, and that's the one I'm going to be focusing on. So, some preliminary qualifications. Penrose admits up front that he's really only arguing against algorithmic artificial consciousness. All bets are off, he says, about analog computation or quantum computation. His proof, his conclusion is directed just at kind of standard digital computers and that kind of algorithmic computation. I'll just flag that if my argument here is correct, or my rebuttal to his argument is correct, then actually he's too modest on this point. I think I can show that analog computation and quantum computation fail in the same ways that digital computation fails. Even though I don't think ultimately that means that there cannot be a simulation of a computational simulation of conscious behavior. So I think the same conclusion that he draws for analog and for classical computation can be drawn for analog and quantum computers. Yeah. Yeah, I know. I'm going to say lots of crazy things. I'm really going out on many branches here because just one of these things would be controversial enough to be pounced on, and I'm going to say a lot. So there's plenty for everyone to feast on here. So I argue. Here's a point that I want to make, but I'm just going to ignore it because I can't talk about this topic without making this point. So I have to make this point and then ignore it. I argue elsewhere that the diagonal argument's emphasis on algorithms also renders the argument impotent even against classical digital computation for this reason, is that, yes, we can do more than algorithms can, but computers can do more than algorithms can. So we mustn't mistake the map with the territory. Algorithms are the ways we try to understand these physical things called computers. And if you show that there's a technical limitation of algorithms, that doesn't mean you've necessarily shown that there's a technical limitation of the things that we understand in terms of those formal models. But I'm not going to rely on that argument. I'm not going to say any more about it now. So back to premise one, the main part of the argument, really. So in particular, there's this, you might call it the non-halting problem. Will Turing machine M not halt when given n as input? That's the question that we're looking at. Let's look at a special case of that, the self non-halting question. Will Turing machine n not halt when given n as input, roughly? There's a little bit of issue there about encoding n, encoding n in the right way so you have turned two arguments into one, but I'm not going to go into that. But roughly, we're looking at this special case. Will Turing machine n not halt when given its own Turing machine number as an input? And I'm not going to explain the enumeration of Turing machines here. I'm assuming, if I'm assuming you're with me on that. Well, there's a theorem that no Turing machine can, that's sound with respect to this question, can answer this question correctly for all n. If it's the sound procedure for answering this question, then it's no Turing machine, well, then any Turing machines that are sound with respect to this question cannot answer it correctly for all n. Why? Well, in particular, any candidate Turing machine for answering this question correctly for all n will trip up when, in the special case where n is its own, oh yeah, well, I'm already considering the self-halting question, when it basically trips up on its own, when n is its own Turing machine number. So if the Turing machine has a number k, then it might be able to do very well for when n isn't equal to k, but at the very least, when n equals k, it will be incapable of giving the correct answer. And I use this diagram to show people why. And I think maybe Sir Roger would find it interesting I use a diagram with some dots here in order to get people to see the truth. Well, actually, Joseph might think that's an interesting point. So what we have here are here's an enumeration of all the possible Turing machines down on the left-hand side. So we have the first Turing machine, the second Turing machine, third Turing machine, so on. And here are the arguments that we give to those Turing machines. That's n. So that's the, we're asking, in this case, we're asking the first Turing machine, does Turing machine number one halt when given one as input? Over here we're asking the second Turing machine whether the third Turing machine does not halt when given 3 as input. Okay. The special case happens on the diagonal, of course. Hence, that's why we call it diagonalization. The idea here is that there cannot be any, this is a proof that there cannot be any Turing machine which answers this correctly for all n, because let's suppose that there were one, let's call it the kth Turing machine. It will have to eventually consider its own case, and it will have to halt if and only if the kth Turing machine does not halt when given input k, and that's a contradiction. So it cannot halt. You and I just determined that it cannot halt, so we can see that it does not halt if it is sound. So you just have now been able to do something that the Turing machine itself cannot do. You've been able to see and mathematically establish, using rigorous methods, that the kth Turing machine, if it's sound with respect to this non-halting question, will not halt when given input k. And that's, you seeing that is the counterpoint to the fact that no Turing machine is capable of giving the right answer for all inputs n. Yet you can for arbitrary n. You know that's true for any k. I didn't give you a specific k, I gave you k in general. You now know for any k, if it's a sound Turing machine with respect to the non-halting question, it will not halt. Because if it did halt on its own number, it wouldn't be sound with respect to the question. So, right, I've already made that point. So therefore, the conclusion is humans cannot be using an algorithm. We went through all the algorithms. None of them none of the sound ones can give the right answer for all n. We can. So therefore, we cannot be using any of the enumerated algorithms. I'm going to concede that point. Let's look at the next premise, though. Since we're not using an algorithm when answering the self-non-halting question, therefore, no computer can fully behave like or simulate a conscious human. Well, I don't think the consequent follows from the previous point or from the antecedent. So, why? Well, in general, this is weak, but in general, there's more than one way to produce the same behavior. So it might not be that we are using any of those algorithms, but we might nevertheless be producing behavior that the algorithm could produce. Right? Just because we're not using the algorithm doesn't mean that the behavior can't be the same. And I'm going to give a constructive explanation of that general point right now. So even if there are questions that we can answer correctly, that no TM can answer correctly, this does not mean that Turing machines cannot perfectly simulate us. So even if we don't have identity of computation here, it might be a simulation relation. I'm going to explain that, how that's possible in a second. In particular, I think there are different senses of behave like or simulate, and in the sense that really matters to the question about AI, premise 2 turns out false. It turns out that even though we can do more than any algorithm, algorithms can nevertheless simulate us. So, why is that the case? So to see what's wrong with that premise 2, note that why is it that the self-non-halting question is non-computable by Turing machines in any way? And why is it that we can answer it? Well, both of those facts, I claim, arise solely from the fact that Turing machines or algorithms or computations are referred to in the self-non-halting question. The question, does the nth Turing machine not halt when given input n? Mentions Turing machines, right? It's a question about Turing machines. So I think that's why Turing machines end up not being able to answer it, and it's why we can, because we don't encounter ourselves on the diagonal, because it's not about us, right? We're not one of those n Turing machines, or to assume we were would be to beg the question. But the idea here is if we define a comparable question that instead of making reference to Turing machines makes reference to persons, you could call it the person's self-non-halting question, then the same discrepancy between humans and Turing machines will arise, only in reverse. There'll be questions that we will be prevented from answering correctly if we are sound with respect to the question, but Turing machines will not have any obstacle to answering that if it's about persons rather than Turing machines. So, for example, enumerate all the questions of English of finite length, enumerate all the people who are alive, your number is n, we play a game, I'm going to ask you questions, you're not allowed to ever give a false answer, and you can only answer yes or remain silent. It's the equivalent of halting or not halting. And I ask you a question, it's the kth question in the enumeration. The kth question happens to be, does the nth person not answer yes to the kth question? Where k is the number of that question. So you will be unable to answer yes to that question correctly, so you must remain silent. And a Turing machine would be able to go through that reasoning and conclude that all people will be unable to answer this question for all n because they'll all trip up on the special case of when their number comes up in the questions about all the combinations of questions and people answering them. So that's the same result for us, exactly similar result for us as for Turing machines. So what hay do I make of that? Well, like I said, there's no reason why. I mean, maybe they cannot, but we don't have an argument that they cannot. There's no reason why a Turing machine cannot give the right answer to Q sub k. As a matter of fact, since it's finite, we could just construct a Turing machine that gives the right answer. Because there's no mention of Turing machines in this person's self-non-halting question, so there's no contradiction in a Turing machine giving the right answer for all k and all n. So Turing machine might even be able to deduce it from a description of your biology, say. So our inability to answer that question, the person's self-non-halting question, is an artifact of the fact that it refers to us. And that's just like the inability of the Turing machine to answer the original self-non-halting question. It's an artifact of its reference to Turing machines.
Now, you could think that that just strengthens Penrose's point. Not only, there's not just one discrepancy between humans and Turing machines, there's two now. There's the mismatch on the non-self-halting question, and there's a mismatch on the person non-self-halting question. But I think there's a different way of looking at it. Even if the token inabilities of Turing machines and people differ, they may be inabilities of the same type. That is, it might be that we have a our behaviors are described by extensionally distinct functions, say, but actually it might be that they can be characterized by intentionally identical functions. So let me, to motivate that point, let me give you an analogy. Suppose I have a twin, Don, I'm Ron. Note that I can't sit on Ron's lap, right? I can't sit on my own lap. But Don can sit on Ron's lap, right? Does that mean that there's a big difference between Don and Ron, that somehow I can't simulate what Don perfectly because Don has this ability that I don't have? Don can sit on Ron's lap, so therefore I can't simulate him? No, because I have Don has exactly the self-same limitation. Well, it's not exactly the same limitation. It's he can't sit on Don's lap, so it's token distinct, but it's the same type. We each have the limitation that we each cannot sit on our own laps. And I think that's analogous to the limitations of Turing machines with respect to the non-self-halting question and our ability to compute it, and the inability of us to give correct answers for the person non-self-halting question, but the ability of Turing machines to answer, or there not being any contradiction in supposing they can do that. So sometimes Y having different abilities or properties from X is no barrier to Y being a perfect simulation of X. And I might even, this is an aside, it's in parentheses, I'd actually say that sometimes really with the notion of simulation we usually use is that for Y to be a simulation of X at all, it has to be distinct in many ways, or it wouldn't count. As a model of the past has to be in the present. It wouldn't be a model of the past if it were located in the past as well, right? So the heart of the notion of simulation involves differences, but it involves similarities in the presence of those differences. So I'm rejecting the idea that for X to simulate Y, X has to compute the same function as Y. For example, Turing himself didn't prove that universal Turing machines compute the same function as any other Turing machine, as an arbitrary Turing machine. No, each universal Turing machine computes a particular function. It's in the enumeration, whatever, 572, that function, and it just so happens that function 572 allows that Turing machine to simulate any of the other Turing machines, but it's not actually one of those other Turing machines. Its Turing machine number doesn't change. It's still 572 computing this universal function. It's not actually computing the particular functions that it's simulating. So even if there are extensionally construed functions that humans can, but Turing machines cannot answer correctly, doesn't imply that Turing machines cannot perfectly simulate human behavior. We have the same intentionally construed limitations. Neither Turing machines nor humans can solve their respective non-halting questions. So I don't think it's been established that Turing machines cannot simulate human intelligence. And so it might be true that Turing machines cannot, but it cannot be concluded for the reasons that the diagonal argument gives. So this possibility remains open, that Turing machines can compute functions or employ algorithms that constitute perfect simulations of us, even though we are not using that algorithm. So how am I doing for time?
You got 60 seconds, mate.
60 seconds.
Let's say 5 minutes.
So what I'll do is I'll just mention what's in these asides. I won't go through them, but that way, if you're interested in them, I can tell you about them. So I generalize this to the case of question answering systems in general. So it's not just humans and Turing machines. It turns out to be every set of question answerers has a corresponding non-self-halting question that could be defined relative to it. You could even do it for the odd-numbered Turing machines. You could do it for the even-numbered Turing machines. You could do it for example, quantum computers. If you use them as to answer questions, then you can define a non-self-halting question. No, sorry, well, it's not going to be halting, right? It's going to be a non-false. Well, let's call it halting when you don't give an answer. We'll call it non-halting. So even a quantum computer that is being used to answer questions will have a non-self-halting question definable for it. It doesn't matter whether it does it by a physical process that's got lots of great advantages over digital computation. This is a theorem of logic that will mean that it cannot answer the respective non-self-halting question for its class. Same with analog computation. Another aside that I make is that this point doesn't require the sets that I'm defining these question answers to be infinite sets. You can have a finite set of just three question answers, and there will be a non-self-halting question for that set. None of them will be able to, if they're sound with respect to that question, none of them will be able to answer it for all three values because they won't be able to answer it for themselves. So infinity is not required. And yeah, I've already made that point. And finally, last 2 slides. Yeah, so this is it. What about this, the moving beyond? I said Sir Roger's argument was very strong because it was arguing against even the possibility of simulating conscious human behavior. What about a weaker claim, which is just the idea that you could never create consciousness on a computer? A computer could never be conscious. So that's maybe less ambitious to make that claim. Well, I think that it doesn't follow that fully behaving like a conscious human is a requirement for being a conscious being, right? There are many ways to be conscious, and so even if you can't create human consciousness, maybe you could create another kind of consciousness on a machine. And also, if you go back to Don and Ron, in a way, Ron can perfectly reproduce all of Don's abilities, even though and Don can reproduce all of Ron's abilities, even though Don can't sit on Ron's lap, or Don can't sit on Don's lap, but Ron can, and vice versa. And I think similarly, understanding Ron's abilities and inabilities can explain Don's abilities and inabilities, even though they are, as I said, token distinct. So I think even the token distinctness of our abilities between Turing machines or computers and us doesn't mean that they can't be reproduced on the intentional level, and doesn't mean that they can't be used to explain human abilities, for example. Okay, and I think that I need to skip that slide. And thank you very much.
Thank you, Ron. Well, wow, what a finish. I think I'm gonna let Roger take the first question.
Well, let me just say this is not the first talk at this conference that I haven't understood. I'm very, of course, you've read this book more recently than I have. I don't recognize the argument that you've given. What are you enumerating when it comes to people? It seems to be sentences, or?
I enumerated all the finite sentences of English, and I enumerated all the people, and then by doing that, you can generate a set of questions, such as, does the nth person in the person enumeration not answer yes when they are given the kth question in the question enumeration? And some of those questions will be about that question is in the enumeration of questions, right? So eventually people will come across it, and if I say, basically I'm saying, is your answer to this question no? And if you only have the options of answering correctly or being silent, you have to be silent.
But all of these questions would be so long and complicated that nobody could be able to answer any of them.
No, I said a finite length, so let's just push the length down to of less than 100 words, of less than 50 words.
I still haven't understood it. Let me make one comment before getting back to this, because, as I said, I have to look at what I'm saying. I don't quite see how you can apply the enumeration to people when, algorithms, you can see, and they're written in the code, and you can enumerate them. people. I don't see there's nothing to do with it. But let me go back, because in my view, the argument I gave yesterday is really, I mean, rather than talking at length, in fact, the argument I gave yesterday is in Shadows of the Mind, as far as I remember.
Sure.
But
that was my last slide that I wanted to skip over. So it's this, when I talked to you in Tucson about this in 2018, and I didn't even have that much time to explain to you. So you almost certainly I didn't make it clear then either what I was getting at. But you said, okay, maybe, but really I'm not. That's not my main argument against AI anymore. My main argument against AI are things like the chess problem, where it's clear that we can see, and somebody who understands chess can see that white can force a draw as long as they don't screw it up, right? They don't need to screw it up. Black can't force them to screw it up. So all they have to do is just maintain their pawn wall. Black has all its pieces trapped in that pocket, and black can't win.
I don't think I would have said the chess one was the
okay.
convincing argument. I mean, it's more the one that if there is an algorithm which gives you true answers to these. Well, I mean, the Gödel argument, the main people object to the Gödel argument is that you don't know what you're. If we are controlled by algorithms, that we don't know what that algorithm is, and so therefore you can't use it.
Yeah, I didn't make that.
So the argument that I was given yesterday was basically that it can't be any. I mean, how could such an algorithm that we don't know, which gives correct answers to mathematics, arise by natural selection?
Right. No, that's why I granted you the knowability. There is no knowably sound algorithm that underlies our mathematical understanding. But what I then went on to say was that, nevertheless, an algorithm could perfectly simulate our behavior. There's no argument against an algorithm perfectly simulating our behavior, because...
Well, of course, because you could just imagine all the humanity that's ever existed and every sentence that anybody has made, and then you just do a different one. I mean, what you just said is obviously true, but it's not really relevant.
Well, I was hoping it would be relevant because it would demonstrate that we have the same kind of limitation about not being able to answer that kind of question. Is your answer to this question no? You can't answer it correctly. That's the same question that the Turing machine is being asked. Can you answer this? Can you not halt when given this number as input? And if it halts and says, yes, I cannot halt, then it's wrong. So if it's going to be true, then it has to not halt. And so it can't give an answer in that question.
No, what I'm saying is that it's obvious that assuming that the number of human beings that have ever lived is finite, which I assume is obvious, and the number of sentences that any human being has ever uttered is finite, and then you just write down some sentence which nobody's ever said. I mean, long enough. I don't quite see what that's proving.
But Ron, before you reply, can I just see if there's any other sort of questions to just pull in and broaden the conversation a little bit? Demis?
Yeah, I'm not very convinced about the original diagonal argument at all. So perhaps I can just ask why. Like, it hinges on this idea of, what does it mean the human can do that? Like, I don't quite understand what that means with respect to these algorithms. I mean, you set up a fairly trivial paradox, basically, of the form, this statement is false, sort that out to the machine, and it can't. But what does it mean by, it can't take itself as an input, and then this just sort of variation on the halting problem. But what does it mean that the human to be able to solve that?
We can see that that no Turing machine can answer that question correctly.
Yeah, I think a Turing machine could also see that, even if it can't answer the question. I mean, you're saying from a macro level, the human can see that the setup there's a flaw in the setup. Is that what we're saying by the human can do it?
The convention is that the way a Turing machine models our understanding is it halts and gives an answer when it can, and if by doing so it would give an incorrect answer. Instead, it must not.
I understand that. You've just set up a trivial paradox, but what does it mean to say the human can do that? I'm trying to understand that part of it. That's what this whole argument hinges on. Are we saying that the human...
No matter which key I give you, you will know that if K is the number of a Turing machine that's sound with respect to the non-halting question, you know that it doesn't halt when given input K.
Okay, so you're saying a human can understand that?
You can, and you now know for all n. You now are able to answer it for all n.
I think a Turing machine could also understand that for all n, even if it can't actually take its own input and it won't halt.
Right, it understands the general.
The meta problem. Why not? That's what the humans do.
It can assent to the general.
Yes, which is all the humans doing as well.
So Roger has a dialogue between him and a computer that it looks like the machine understands it, but when you actually ask it, well, okay, well, go ahead. Then what is it for K? You give it its own Turing machine number, and it will have to just remain silent.
I don't think a human can do that in if you enumerate every program either. I think the human can do it in general, in the general case, and I think a Turing machine could as well. There's nothing in that setup that doesn't allow that. Okay. I'm just saying the definition that the human can do it is a very vague, it's all hinging on that. And I think what we're meaning, as far as I can understand it, maybe I'm misunderstanding it because I haven't read Shadow's in the Mind, but is that the human can understand the meta problem. There's a paradox there. Not that a human can actually enumerate every single program. I don't think.
Again, defending.
I mean, that's sort of
no matter what number you give to a human, because you've grasped the general proposition, right, that is true for. Okay, I could give you one now. I could say 1.32 times 10 to the 25th, and you'll say if that's the Turing machine number and if it's sound with respect to the non-halting question, no, it doesn't halt. Whereas if that happens to be the Turing machine number. Whatever number Turing machine that is the Turing machine number of, it will not be able to say that it does not halt, because if it did, it would be being unsound. So
I think this is a straw Penrose, isn't it?
Folks, any other questions at this point? Because would anyone like to ask anything at this point, or do we move to concluding? Our sort of visiting guests of honor have arrived. We have the rector of University of Turku, who's kindly been helping us set this up, and we have some of our wonderful local bankers here who've come to see what's happening at Kankas and what we're doing here. And we of course have the chairman of the EMI Network Foundation here, Carl Gustav. So I thank all of you guys for coming. Ron, I think that's very provocative. If there are no further questions, I want to say this. I think that Demis actually, there is more to it than that. And it has to do with the notion of how we know that we're experiencing truth and why. I'm not saying that we cannot make a machine of some description that can do that, but it's unclear to me what that machine would look like. I think the newness of Ron's argument, as far as I can see, is essentially the idea that maybe we could make a machine using a Turing machine that can simulate those experiences sufficiently so that it can have this kind of experience of truth that's similar enough to mine or yours, that then in a way we can no longer rely on this argument about sort of, but it's not just a simple paradox. I mean, the notion is in the way that we have this, we have some system R, we construct a proposition in it, we all immediately, we rely on R and our experience and say it's not true. Or it's true, right? And then actually we can also simultaneously show that there's no algorithmic means to construct them. I want to say further that there is, I think, some very good points raised by folks like Joseph Almog here about that there's another aspect of this which has to do with things that we cannot maybe modelize. I think Hugh has actually touched on that. So while I definitely want to build one of those machines with you, I think it's going to be hard. But I want to really thank Ron and everybody over the last 2 days. Remember, we still got all night to argue and enjoy ourselves. So I'm going to invite Paavo and Sabrina to come and join me to give some concluding remarks. But Ron, thank you so much. And I think this is like a jazz thing, so we've had precisely 0 minutes to prepare. So should we maybe approach it as 3 perspectives to what has happened here? Because it's, wow, it's a bombshell. I mean, and maybe Paavo, okay, you take the honor of going first.
Okay, I go first. So, yes, I selected some themes here. I think each one of us will have our limited understanding of what took place here. Anyway, so one theme that came here quite strongly was the idea of experience first. So somehow experience, consciousness, being somehow fundamental. I think that came up both in Jussi's talk and also with Tononi. And so that's of course very interesting. It's philosophically, we can do that. And in some ways, of course, it goes perhaps against the common sense, where the common sense might say, well, there's the physical world, and then maybe experience arose at some stage. So in that sense, of course, we've had this strong philosophical component. Another thing we had was this connection between quantum mechanics and consciousness, so quantum mechanics and experience. And of course, that is another, in some ways, of course, a controversial idea, but still an idea that some of us feel kind of attracted for various reasons. It could be non-computability, it could be other things. And of course there, if we say that consciousness is more of the quantum nature, and then, or somehow connected to quantum realm, then that does connect with the idea of experience being fundamental, because quantum could also mean that these things are not fundamental, so that the manifest world is somehow derivative. So I could see their convergence. Now, I think another thing, of course, with mathematics, not my strong area, but I think what I was intrigued was the way people were saying that all these problems of mathematics, we are thinking about them, and that thinking is kind of part of the world. So what does that tell us about the world? We have all this mathematical thinking, and somehow our picture of the world has to explain how come the world is capable of all of this mathematical thinking. And it has to do with, people raise the question of evolution and all those things. So this is a fascinating thing that I learned, or at least was puzzled about here. Amazed, I think we were talking about amazement in the beginning. Of course, there was a lot of discussion on AI, which we heard right now. I think that we don't need summarizing. That's a vibrant and intensive thing. There were also some discussions about radical ideas of possibly going backward in time. Of course, a kind of, I remember we actually had a conference in London 2017 with Hugh Price on retrocausality, and some people there were saying that the idea of retrocausality, like being able to go backwards in time, is against the spirit of science, where Hugh Price said, no, causality is I do something here and something happens elsewhere. That's retro. So, but even that radical idea came up here. So I think that's enough for my part. So please, Sabrina. Thank you, Paavo.
I will give perhaps a complementary view of some of the things that I believe happened here. And the first thing I would like to say is that it was impressive, the variety and the different perspectives and the different approaches to some of the most fundamental questions that are nowadays open, really. And we are talking about understanding the mind, understanding consciousness, understanding deep mathematical problems, understanding quantum physics, understanding gravity. I mean, we are talking really about the foundations of, I believe, understanding itself as a conceptual framework. And of course, we do come from different backgrounds and we do speak different languages, and therefore it is always difficult somehow to grasp what are the main points and approaches. But I believe that through the discussions at the time that we had to spend together, not only here when giving talks, but also when having lunch, at the coffee break, in the evening, I think that we started to create and to reinforce the common language that I think are necessary nowadays to have a fully multidisciplinary approach to tackle these questions, because I think that this is what is really needed. So we need more and more to join forces to build a language and a framework in which we can cooperate to really tackle these problems. And so I would like to see also in the future more and more approaches of this type. And as Jussi said many times during the workshop, this is the beginning of a process. So this is the beginning of something that we hope to continue in the following months, in the following years, and that I believe would reveal to be successful, because I can see here a lot of enthusiasm and a lot of passion for what we are talking about, and therefore I think that is an effort that we all want to undertake.
Thank you, Sabrina. So I echo everything that was said. I mean, Paavo covered very nicely the multitude of things that happened here. And I think, you know, the folks that just arrived can kind of, if you just look at us, it looks like we're coming out of a bomb shelter. It's been a hell of a 2 days. It really has been amazing. And it's been amazing to actually, I mean, many of you I've known for a long time, some of you I'm meeting for the first time. Like Sabrina said, it's great to have everybody together. I won't say this is the beginning of a long process. I sense that Basil and Roger would strongly disagree with me. They've been at it for some time.
I think a few years.
I think we'll all be at it for years to come. I just want to make a few observations. So I think really at the bottom of it all, for sure this is important. So, and in ways that we can't even yet imagine, or we can't even currently imagine. I think if we think about folks in this room who are maybe most responsible for how it's already important in our life today in ways that, you know, you don't have to understand a single thing that got said here today, but this matters to your life, is you only need to look at Demis, right? These conversations we have are not just sort of about fundamental human insight, which is very, very important and certainly one of the big motivating forces for me, but they matter to people's daily lives, right? And it's important also that we're committed to using these insights to make a better world, and Demis spoke beautifully about that, to understand this world around us better, and actually use these capabilities to improve ourselves, you know, to make better medicine, I don't know, to make it easier to drive to work every morning, you know, what have you. And I think it's very, very complicated. And it's very important that in this process we don't accidentally, for example, sterilize ourselves from the things that make us human, even if it turns out that we're Turing simulable. This is sort of, you know what, who cares? But what is very possible is that as we allow more and more of these algorithmic processes to actually guide us through our daily lives, you know, to pick the music you listen to, propose the next book you're going to read, it's very easy that we might accidentally lose something. And it's actually folks like us that have to remain kind of awake and say, hey, this stuff matters in a really, really everyday kind of sense. So I think what we're doing is important. It matters. And it's already making a difference. It's not making a difference, you know, 50 years from now, although I think it'll do that too. It's always lovely to be in a room where people will say things like, you know, on the 1000th anniversary of this conference, you know, and it's just amazing, you know. I mean, we talked about sort of structures that are so vast and sort of so unknown to us. You know, it's amazing to me to be able to spend time with, you know, someone like Roger who spent a lifetime thinking about these things. And then on the last day, him saying, well, I mean, that's just very complicated. I mean, we don't even know anything about that yet, right? So we got a lot of work to do, okay? But basically, I think really at the heart of it is all of us, right? So really, listen, it's very, very clear that lots of experiments need to be made, right? People need to work to define, give good definitions of what those experiments are. The right people need to get connected so we can do those experiments. There's lots of models, right? Both sort of models of fundamental, sort of philosophical kind of saying what's going on here, and then just sort of like really workaday, I mean, I say workaday, I don't know that there are anything particularly workaday here today, but really like, hey, here's some stuff that's going on in the brain. We can model it as this kind of a Bayesian processor. We can model it as this kind of an open quantum network. That work has to keep happening. You know, mathematics has to be more closely coupled. Like our understanding of human experience and human consciousness also definitely includes mathematical experience. It includes computational experience. It includes our experience of the physical world. And all of this work has to get done. None of us is going to pull it off on their own, right? So really it comes down to all of us as people to make sure that this is really sort of a milestone rather than, you know, the beginning or the end of anything. You know, take the time, make the effort. I, for one, you know, anything I can do to advance this goal, and I think I speak for our guests here too, you know, we're ready to do. It's important. It's amazing. You know, some of it is totally mind-blowing. And it's also just really fun. So I want to thank everybody for making a huge effort to be here. And I'm hoping to see everybody again sometime really soon. And now, let's start to wander towards the castle, have some food, listen to some music about the mind and of the mind, which I think would be quite fun. And let's have some supper. So thank you, everybody. Thank you. So I will now lead the coalition of the willing towards the chairman, who will keep leading them towards the castle while I use the facilities.